Welcome to this preparatory course designed specifically to guide you through the GARP Sustainability and Climate Risk Certification. We will start by establishing a solid understanding of the examination structure and the strategic approach required to succeed. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to the Global Association of Risk Professionals, GARP, in any way. This content is for informational and educational purposes only and does not constitute financial, legal, or investment advice. Always consult a qualified professional before making financial or legal decisions. The SCR certification is designed to bridge the gap between financial risk management and the urgent realities of climate change. By completing this program, you will gain the vocabulary and the analytical rigor necessary to evaluate climate-related exposures effectively. We prioritize a deep understanding over rote memorization, ensuring you can apply concepts to real-world scenarios. Our goal is to provide a structured pathway that optimizes your study time and builds your confidence for the actual testing environment. The exam itself consists of 80 multiple-choice questions that cover a vast breadth of material, ranging from physical climate science to complex regulatory frameworks. You are granted 4 hours to complete the assessment, which implies a distinct cadence for how you handle each question. A significant component of the exam is the integrated, multi-part case study, which tests your ability to synthesize information across disparate topics. This is not simply a test of your knowledge regarding definitions, but a test of your ability to manage risk under uncertainty. You must become comfortable with the interdisciplinary nature of the curriculum, where scientific data intersects with financial policy. Weighting is a crucial factor in your study strategy, as the exam is divided into distinct domains that carry different levels of emphasis. Physical risks, transition risks, and regulatory developments are prioritized differently by the GARP curriculum developers. Understanding these weightings allows you to allocate your energy toward the topics that yield the highest return on investment. I strongly encourage you to treat the core readings not as background information, but as the raw data you will analyze during the exam. Success requires a disciplined cadence of reading, reflecting, and applying these frameworks to hypothetical balance sheets and institutional policies. Time management is perhaps the most subtle yet critical challenge for any candidate sitting for a 4-hour exam. Many students struggle because they spend excessive time on the initial questions, leaving insufficient capacity for the rigorous multi-part case studies appearing later. You must learn to identify complex problems quickly and decide immediately whether to solve them or move forward, circling back only when time permits. Practice sessions should simulate this pressure to ensure that your analytical speed is as refined as your theoretical knowledge. Consistency in your preparation will naturally build the endurance required to sustain high-level cognitive performance throughout the entire duration of the test. We will move through each module by examining the core theoretical underpinnings before exploring their practical applications in finance and risk management. My responsibility is to strip away the abstractions and ensure that you understand the underlying mechanisms governing climate-related financial disclosures and risk assessments. You should be prepared to think critically about how institutional decisions impact long-term sustainability outcomes. I trust that this systematic approach will clarify the path forward. I look forward to our next session. Welcome to the Foundations of Climate Change, where we will examine the scientific principles of our climate systems. This chapter provides the rigorous baseline necessary for any professional working within sustainability and climate risk. Understanding the fundamental mechanisms of climate science is not just an academic exercise, but a prerequisite for assessing risk in a warming world. By mastering these concepts, you will gain the ability to distinguish between noise and signal when evaluating climate data, which is exactly why this section is the most critical part of your preparation. We will bypass the superficial narratives often found in mainstream media and instead focus on the empirical data that drives GARP's examination questions. You will learn to navigate the complexities of radiative forcing, greenhouse gas lifetimes, and the nuances of paleoclimate indicators with professional confidence. This course is designed to transition you from a passive observer of climate news to an active, informed analyst capable of parsing complex scientific reports. If you are aiming for excellence on your exam, and want to build a career on a solid, evidence-based foundation, this material is tailored precisely for you. The distinction between weather and climate is foundational to understanding the data we observe, with weather representing the day-to-day state of the atmosphere at a specific location, while climate signifies the statistical average of these patterns over extended periods, typically decades or longer. To look back, we rely on paleoclimate indicators such as ice cores, tree rings, and sediment layers, which utilize isotope analysis to reconstruct environmental conditions from long before humans recorded data. These records demonstrate that the Earth has undergone significant non-anthropogenic changes, driven by factors like orbital shifts, solar radiation variability, and volcanic activity. By distinguishing these natural cycles from contemporary warming, we can isolate the specific impact of human activities on the current climate trajectory. Understanding this historical context prevents us from misattributing natural variability to anthropogenic causes, or vice versa, ensuring our risk assessments remain grounded in objective reality. This scientific rigor is the bedrock upon which you will evaluate future climate scenarios and policy interventions. At the center of climate change sits the Earth's radiation balance, an interplay of incoming solar shortwave radiation and outgoing terrestrial long-wave infrared radiation. Certain gases in our atmosphere act as a thermal blanket, trapping heat and preventing it from escaping into space, a process known as the greenhouse effect. Radiative forcing acts as the quantitative measure used by scientists to define the influence that specific factors have on the net change in the Earth's energy balance. When we increase concentrations of greenhouse gases, we increase the positive radiative forcing, leading to a net gain in energy that manifests as rising global mean temperatures. This is not a matter of debate, but a statement of physical chemistry and thermodynamics that governs how our planet retains heat. By understanding the energy budget, you can better conceptualize how policy decisions, such as carbon pricing or emission caps, directly influence the physical climate system. Different greenhouse gases have varying capacities to trap heat and different residence times in the atmosphere, characteristics that dictate their overall climate impact. Carbon dioxide remains the primary driver of long-term warming due to its overwhelming volume and longevity, despite having a lower heat-trapping potential per molecule when compared to other gases. Methane possesses a significantly higher global warming potential over shorter time horizons, making it a critical focus for immediate climate mitigation strategies despite its shorter atmospheric lifetime. Nitrous oxide, while emitted in smaller quantities, remains potent due to its chemical stability and long life, while fluorinated gases, though emitted in trace amounts, are exceptionally potent, often serving as critical focal points for industrial regulatory standards. Furthermore, we must account for aerosols and particulate matter, which can have complex effects. Some, like sulfates, reflect sunlight and provide a temporary cooling effect, whereas black carbon absorbs heat and accelerates warming in specific regions. Balancing these diverse variables is required to project future warming and to assess the sensitivity of global financial markets to regulatory shifts. I look forward to discussing how these mechanisms interact in our next session. Welcome back. In this lesson, we explore global warming potentials as the primary metric for standardizing how we account for diverse greenhouse gas emissions in a climate risk context. To effectively manage climate risk within a corporate or financial framework, we need a common language for emissions. Carbon dioxide is the reference point, but industrial activities release a cocktail of gases like methane, nitrous oxide, and various fluorinated compounds, each with distinct physical properties. Global warming potential, or GWP, serves as an index that allows us to normalize these gases into a single unit, known as carbon dioxide equivalent. This metric is essentially a measure of the cumulative radiative forcing, or heat trapping effect, that a given mass of a gas exerts over a specific time horizon compared to carbon dioxide. Without this normalization, comparing the relative climate impact of a fugitive methane leak to the CO2 emitted from a coal-fired power plant would be mathematically impossible. The physics behind this relies on two primary factors: the radiative efficiency of the molecule and its atmospheric lifetime. Radiative efficiency describes how effectively a molecule absorbs infrared radiation, while the atmospheric lifetime dictates how long the molecule remains active before it is broken down or removed from the environment. Because these gases degrade at vastly different rates, the time horizon chosen for the GWP calculation, most commonly 20 or 100 years, significantly alters the resulting values. A gas like methane has a much higher GWP over 20 years than it does over 100 years because it is relatively short-lived. It traps a massive amount of heat quickly but disappears, whereas CO2 lingers for centuries. Practitioners must be diligent in specifying which time horizon is being used, as reported emissions inventories can look drastically different depending on the baseline selected. While GWP is the industry standard for reporting under frameworks like the Greenhouse Gas Protocol, it is not the only way to model these impacts. Global Temperature Change Potential, or GTP, offers an alternative approach that focuses on the temperature change at a specific future point in time rather than cumulative integrated radiative forcing. While GWP prioritizes the total energy balance, GTP estimates the actual deviation in global mean surface temperature resulting from current emissions. For professionals dealing with carbon accounting and regulatory disclosures, understanding these metrics is not merely an academic exercise, but a core competency for risk assessment. When you aggregate an organization's Scope 1 and Scope 2 emissions, you are aggregating various species of gases into a unified carbon footprint, which then informs everything from carbon tax liabilities to internal shadow pricing. If an industrial sector relies heavily on synthetic refrigerants with high GWP values, their climate risk profile shifts significantly based on the metric used to evaluate their transition path. Large-scale decarbonization strategies rely on these metrics to prioritize interventions, often focusing on high GWP gases that provide the most immediate mitigation potential. By converting diverse environmental impacts into a standardized equivalent, institutions can integrate climate impacts directly into financial models and risk management systems. This creates a transparent and comparable data layer that stakeholders, regulators, and investors demand when assessing the environmental integrity of transition plans. I will see you in the next lecture. Welcome back. In this lesson, we explore the nonlinear dynamics of our climate system by examining how feedback loops and critical tipping points act as amplifiers for global warming. To understand the climate system, we must move beyond simple linear models of temperature increase and look at the mechanisms that can cause abrupt changes. Climate systems are governed by complex feedback loops, which can be either positive or negative. A negative feedback loop is a self-regulating mechanism that offsets a change, such as clouds reflecting sunlight back into space as water vapor levels increase. Conversely, a positive feedback loop reinforces the initial change and accelerates warming. When these reinforcement loops become self-sustaining, we move toward critical thresholds known as tipping points. A tipping point represents a qualitative change in the state of a subsystem where a small perturbation leads to a large, often irreversible shift. From a risk management perspective, these points are essential to monitor because they represent fat tail risks where the impacts are catastrophic and the ability to intervene diminishes rapidly once a threshold is crossed. A significant focus area for the exam is the thawing of Arctic permafrost, which functions as a massive reservoir of organic carbon accumulated over thousands of years. As the surface air temperature rises, the ground thaws, and microbes break down this previously sequestered organic matter. This process releases carbon dioxide and, more importantly, methane, which has a significantly higher global warming potential than carbon dioxide over shorter time horizons. Once the permafrost begins to thaw on a large scale, the released greenhouse gases drive even more warming, which causes further thawing. This runaway positive feedback loop is difficult to reverse because the planetary system no longer relies solely on anthropogenic emissions to drive temperature increases. You should recognize this as a systemic risk because the geographical scale makes local mitigation efforts ineffective once the process reaches a certain level of intensity. Similarly, the collapse of major ice sheets demonstrates how albedo feedback loops function within the cryosphere. Earth's ice sheets, such as those in Greenland and West Antarctica, reflect a large portion of incident solar radiation back into space. As warming causes these ice sheets to retreat, darker land or ocean surfaces are exposed, which absorb more heat and further accelerate the melting process. This loss of ice also leads to sea level rise, creating physical risks for global economies that depend on coastal infrastructure. Another critical subsystem is the Atlantic meridional overturning circulation, which is a key component of global heat distribution. If the influx of fresh water from melting glaciers disrupts the salinity of the North Atlantic, the circulation could slow down or collapse. A slowdown of this intensity would fundamentally alter weather patterns, affecting agricultural productivity and disrupting established economic sectors in the Northern Hemisphere. The dieback of the Amazon rainforest illustrates how ecological tipping points intersect with regional climate regulation through vegetation climate feedbacks. The Amazon is not just a carbon sink, but a hydrological engine that recycles moisture throughout the continent. As deforestation and global warming push the region past a critical dry threshold, the forest may lose its ability to sustain its own canopy. This transition from a rainforest to a savanna state would release vast amounts of stored carbon into the atmosphere, transitioning a major global carbon sink into a carbon source. Because these subsystems are deeply interconnected, the failure of one can increase the likelihood of triggers in another, leading to a cascade of environmental shifts. When analyzing climate risks, it is insufficient to consider only incremental temperature changes. You must also evaluate the probability and potential impact of these irreversible, self-reinforcing dynamics within the broader climate system. See you in the next lecture. Hello and welcome. In this session, we will examine the structure and scientific significance of the core IPCC assessment reports to help you master the foundational data required for the exam. The Intergovernmental Panel on Climate Change serves as the primary scientific authority on climate change, producing comprehensive assessment reports that aggregate global knowledge through a rigorous, peer-reviewed process. You should view these reports not as mere academic documents, but as the fundamental data sets upon which all climate risk models and institutional policies are built. Each report is divided into three distinct working groups, each focusing on a specific dimension of the climate crisis. Working Group I addresses the physical science foundations, providing the raw data on atmospheric changes and greenhouse gas concentrations. Working Group 2 focuses on impacts, adaptation, and vulnerabilities, detailing how biological and human systems are currently responding to these shifts. Finally, Working Group 3 evaluates mitigation strategies, providing the technological and economic frameworks necessary to reduce emissions and limit warming in accordance with planetary boundaries. Understanding this tripartite structure is essential for any professional tasked with interpreting climate change projections for organizational strategy. To translate global climate science into actionable risk management, the IPCC employs specific methodological frameworks known as representative concentration pathways, or RCPs, and more recent shared socioeconomic pathways, or SSPs. These pathways are essentially narrative scenarios that model how different levels of greenhouse gas emissions, combined with various social and technological development trends, lead to vastly different temperature outcomes by the end of the century. RCPs focus on radiative forcing targets, while SSPs integrate the socioeconomic drivers, such as population growth, energy consumption, and international policy cooperation, that determine whether those forcing targets are achievable. For a risk professional, these pathways function as the input variables for scenario analysis. If you cannot correctly identify which pathway a particular risk model assumes, you cannot accurately assess the potential for stranded assets or physical peril. Grounding your understanding in these pathways ensures that the climate risk assessments you perform are aligned with the most authoritative and widely accepted scientific projections available today. When we examine the concept of carbon budgets, the IPCC provides the mathematical limit on the amount of carbon dioxide that can be emitted globally while maintaining a reasonable probability of staying beneath a specific temperature threshold, such as 1.5 or 2 degrees Celsius. These budgets are finite, necessitating a brutal reality check for institutional planning, as they dictate the pace at which the global economy must decarbonize. When you assess corporate transition plans, you are effectively measuring how a firm's stated carbon reductions align with these remaining global carbon budgets. If a company claims to be aligned with net zero goals while relying on production trajectories that exceed the remaining carbon budget for their specific sector, you are likely looking at a potential liability risk or a strategic inconsistency. By mastering how to derive and interpret these budgets from the core reports, you gain the ability to interrogate the validity of environmental claims made by institutions and governments alike. See you in the next session. Welcome back to our journey through the GARP SCR curriculum. In this lesson, we will explore the uneven distribution of physical climate impacts and their subsequent economic consequences across global systems. To understand the geographical dimension of climate risk, we must start by acknowledging that the physical impacts of a warming planet are seldom uniform. While climate change is a global phenomenon, the manifestation of precipitation volatility and acute weather intensification varies significantly, depending on latitude, topography, and proximity to major oceanic basins. Countries in the tropics may face drastically different challenges compared to those in mid-latitude regions, particularly regarding monsoon patterns and the frequency of tropical cyclones. Furthermore, chronic risks like sea level rise create an existential stressor for coastal regions and low-lying island nations, while landlocked areas might experience acute threats related to desertification and water scarcity. This regional sensitivity implies that institutional asset exposure is inherently local, necessitating a nuanced approach to risk assessment that transcends national-level averages. A standardized metric applied across a global portfolio can mask critical vulnerabilities that only appear when we consider the specific geographical context of an asset. These physical disruptions naturally flow into socioeconomic systems, causing damage that ripples through global supply chains. When extreme heat or flood events compromise critical infrastructure, the result is often a multiplier effect on local economic output that lasts far longer than the duration of the weather event itself. In the agricultural sector, for instance, localized crop failures driven by drought or uncharacteristic precipitation cycles do not merely impact the immediate farming community. They induce price volatility in global food markets and disrupt the upstream logistics of multinational corporations. Similarly, we must consider the decline in human labor productivity as a direct consequence of rising heat stress, particularly in emerging economies where reliance on outdoor labor remains high. As public health systems face the strain of these heat-related crises, the resulting economic cost increases the burden on regional governments, further eroding the fiscal stability that protects private investments. When these localized economic failures cross a certain threshold, they frequently act as catalysts for mass human migration, forcing us to view climate risk not just as an environmental factor, but as a structural driver of social and geopolitical instability. The implication for financial institutions is that the traditional assessment of geographical risk must shift toward a more granular, bottom-up model of vulnerability profiles. When a bank evaluates the resilience of its lending portfolio, it needs to map those assets against high-resolution climate projections to identify regions that lack adaptive capacity. Infrastructure damage is not just a structural risk, it is a credit risk when the surrounding economic ecosystem becomes unviable due to chronic environmental degradation. Biodiversity loss further complicates this picture, as natural capital, such as wetlands or mangroves, is often the primary defense mechanism against acute weather events. By failing to account for the degradation of these natural buffers, financial models consistently underprice the true cost of regional climate vulnerability. As we move forward in our analysis, we must keep this interplay between regional physical reality and systemic economic instability at the forefront of our risk management strategies. Evaluating corporate exposure requires us to recognize that a business entity cannot thrive in an environment where its essential geographical and social systems are in a state of rapid flux. We'll see you in the next lecture. Welcome back. In this lesson, we explore the strategic dichotomy between mitigation and adaptation as the primary mechanisms for managing climate change outcomes. Mitigation focuses on the root causes of climate change by reducing or preventing the emission of greenhouse gases. The primary lever here is the rapid deployment of renewable energy sources such as wind, solar, and geothermal, which serve to displace carbon-intensive fossil fuel combustion. Beyond energy supply, industrial energy efficiency stands as a critical pillar, necessitating the optimization of manufacturing processes and the electrification of heat. Carbon capture and storage represents a sophisticated technological intervention, allowing for the sequestration of carbon dioxide at point sources or directly from the atmosphere before it contributes to radiative forcing. Furthermore, nature-based solutions, such as reforestation, wetland restoration, and soil carbon sequestration, provide dual benefits by acting as carbon sinks while simultaneously enhancing biodiversity. These strategies require systemic coordination across both private sector investment and government policy to reach the necessary scale for achieving net zero objectives. Balancing these technological and natural interventions is complex, as each carries distinct trade-offs regarding cost, scalability, and long-term retention of carbon. While mitigation seeks to curb the source of the problem, adaptation aims to moderate the severity of the impacts that are already occurring or are now considered unavoidable. Infrastructure resilience planning is the cornerstone of this approach, requiring firms and governments to stress test assets against extreme weather events and shifting climate patterns. This involves hardening logistics networks, updating urban planning codes to handle sea level rise, and investing in drought-resistant agricultural technologies. However, risk practitioners must be wary of the phenomenon known as maladaptation. This occurs when a short-term intervention, such as building a seawall to protect a specific coastline, inadvertently causes greater erosion elsewhere or encourages development in a high-risk zone, ultimately increasing vulnerability over the long term. Effective adaptation requires a holistic approach that considers interconnected ecosystems and socioeconomic systems rather than isolated asset protection. It is a continuous process of iterative risk assessment rather than a static completion of a single project. The frontier of climate response includes various geoengineering concepts designed to alter the Earth's system directly, categorized broadly into carbon dioxide removal and solar radiation management. Carbon dioxide removal technologies involve methods like ocean fertilization or direct air capture, which are conceptually attractive because they address the concentrations of greenhouse gases directly. However, these methods are currently plagued by high costs, unproven long-term viability, and potential ecological side effects on marine or terrestrial chemistry. Solar radiation management proposes reflecting a portion of sunlight away from the Earth's surface, for instance through stratospheric aerosol injection, to induce cooling. While this could theoretically lower global temperatures rapidly, it introduces extreme governance challenges and risks altering global precipitation patterns in unpredictable ways. Furthermore, such technologies do not solve ocean acidification, as they do not remove the carbon already dissolved in the water. Relying on these unproven technologies creates a moral hazard, potentially weakening the incentive for firms to invest in essential, proven mitigation and transition strategies. See you in the next session. Welcome back. In this chapter, we explore the conceptual history of sustainability and how the language of non-financial reporting has shifted to define modern corporate value. The evolution of sustainability framing is not merely a change in terminology, but a fundamental shift in how markets perceive the relationship between a firm and its environment. Historically, corporations viewed social and environmental concerns through the lens of corporate social responsibility, which often functioned as an add-on or a peripheral philanthropic activity. These initiatives were frequently divorced from the primary business model, serving largely as a tool for public relations rather than as a core business strategy. Over the last 2 decades, however, this framing has moved from the periphery to the center of financial valuation. We now recognize that non-financial factors such as carbon emissions, labor practices, and board diversity act as early warning systems for systemic risk. This transition marks the move from viewing sustainability as a cost center to viewing it as a driver of operational resilience. By integrating these metrics, firms aim to protect long-term capital and ensure that they remain viable in a world where regulatory and physical climate risks are increasingly material. To understand the current dominance of environmental, social, and governance, or ESG metrics, we must acknowledge the failure of voluntary frameworks to provide consistent, cross-sector comparability. In the early stages of sustainability reporting, companies adopted various standards, leading to a fragmented landscape where information was often opaque and difficult to verify. This lack of standardization made it nearly impossible for institutional investors to determine how environmental factors influenced a company's fundamental financial health. When we discuss ESG integration, we are effectively discussing the systematic assessment of risks that traditional accounting standards previously ignored. Governance, as the third pillar, acts as the mechanism for oversight, ensuring that companies have the appropriate controls in place to manage environmental and social risks effectively. Without a robust governance structure, Any effort to address climate or social issues lacks the institutional weight required to affect real change at the board level. Consequently, the framing has evolved to emphasize that these factors are not externalities, but are actually core drivers of financial performance. The modern framing of sustainability focuses heavily on the concept of financial materiality, which is the idea that an issue is only relevant if it has a measurable impact on a firm's financial condition. Investors are progressively demanding data that translates non-financial risks into potential profit and loss scenarios. For instance, a firm's inability to manage its transition to cleaner energy sources could imply a future liability, effectively stranded assets, or decreased market competitiveness. This logic necessitates that corporations disclose how climate risks explicitly impact their cash flows and capital expenditures over long horizons. By framing sustainability through the lens of risk mitigation and value creation, firms provide stakeholders with the data necessary to evaluate long-term corporate viability. This transition has turned sustainability into a language that finance professionals can speak fluently, bridging the gap between moral imperatives and hard bottom-line results. As market participants continue to refine these models, the focus shifts towards standardizing the disclosure of these indicators to improve the overall quality of investment decision-making. See you in the next lecture. Welcome back to our journey through the essential frameworks you need to master for your certification. In this session, we will examine the United Nations Sustainable Development Goals as a structural blueprint for global sustainability and their practical application in finance. The Sustainable Development Goals, commonly referred to as the SDGs, represent a universal mandate established by the United Nations in 2015. These 17 interconnected goals provide a shared framework for peace and prosperity for people and the planet, both now and into the future. From a risk management perspective, they serve as a taxonomy for identifying systemic challenges that have tangible economic implications. While they are often viewed through a philanthropic or social lens, for the SCR candidate, they represent a set of non-financial risks that eventually manifest as financial risks. Effectively integrating these goals requires an understanding that each target sits within a broader ecosystem of macroeconomic stability. When a corporation or a sovereign state fails to meet these objectives, it often indicates underlying weaknesses in governance, long-term resource management, or social cohesion. Financial institutions play a critical role in this ecosystem by mapping their capital allocation against these 17 pillars. By aligning investment portfolios with specific SDGs, firms attempt to mitigate negative externalities that could otherwise jeopardize long-term returns. For example, investment in renewable energy might map to SDG 7 regarding affordable and clean energy, while simultaneously addressing climate mitigation strategies that protect asset values against future policy shocks. However, this mapping process is not merely about tracking positive impact. It involves a rigorous assessment of how current investment practices might inadvertently exacerbate other goals, such as water scarcity or income inequality. Professional risk management now demands that we look at an investment's footprint across these goals to ensure that we are not solving for one metric while creating a systemic risk elsewhere. When we analyze sovereign risks through the lens of the Sustainable Development Goals, we gain a unique vantage point on macroeconomic stability. Countries failing to make progress on goals related to education, infrastructure, or environmental quality are frequently susceptible to prolonged economic stagnation. Investors utilize these performance indicators to adjust sovereign credit risk assessments, as a lack of sustainable development often correlates with higher political risk and reduced economic resilience. In emerging economies, the gap between current development and the SDGs can be quite wide, presenting both significant risks and substantial opportunities for sustainable finance. The challenge for a risk manager is to quantify how specific gaps in national development targets might translate into volatility for local currency bonds or equity markets. This requires moving beyond traditional GDP analysis to incorporate data on human capital and social safety nets. The integration of these goals into corporate strategy helps firms manage their operational resilience by identifying potential bottlenecks in their supply chains. If a multinational corporation relies on raw materials sourced from regions struggling with SDG 6, the goal concerning clean water and sanitation, their long-term operational continuity is at risk. By framing these issues as strategic enterprise risks, boards are now more likely to allocate capital toward remedial actions that protect the bottom line. This shift represents a transition from viewing sustainability as a public relations endeavor to treating it as a prerequisite for institutional longevity. Analysts must therefore evaluate whether a company's disclosed sustainability targets align with the specific challenges identified in their operational footprint. When these are misaligned, we frequently encounter the risk of reputational damage or regulatory scrutiny, which ultimately affects the enterprise value. As you prepare for the exam, remember that the SDGs are not merely a checklist, but a complex network of cause and effect relationships. You should focus on understanding how the failure to achieve one goal can trigger a cascade of failures in others, thereby increasing the level of risk within a given portfolio. The ability to identify these linkages allows an analyst to speak the language of sustainable finance with precision and authority. We will see how these concepts form the bedrock of the more quantitative risk management approaches we cover in later sections. Keep this interconnected model in mind as we proceed to our next technical deep dive. See you in the next lecture. Welcome to our exploration of natural capital and its inextricable link to corporate stability. We will examine how the degradation of ecosystems creates systemic risk that every financial professional must now account for. In this chapter, we pivot from the singular focus on atmospheric carbon to the broader biological foundations of our economy. You will discover how the concept of natural capital treats the environment as an asset class capable of generating a flow of services over time, much like traditional financial capital. We categorize these ecosystem services into four distinct domains: provisioning, regulating, cultural, and supporting services. Provisioning services involve the raw materials we extract, such as food, timber, and medicinal plants, which form the bedrock of many global supply chains. Regulating services are perhaps more subtle yet vital, including carbon sequestration, water purification, and pollination, all of which maintain the baseline conditions for stable economic activity. Cultural services provide intangible benefits like landscape aesthetics and recreation, while supporting services such as nutrient cycling and soil formation are the fundamental processes that allow all other ecosystems to function. Neglecting these services introduces profound volatility into balance sheets because when biological infrastructure fails, these services are not easily or cheaply replaced by capital expenditure. The current crisis involving biodiversity loss represents a fundamental shift in how we must interpret corporate viability and long-term value. Biodiversity is not merely an environmental concern, but a prerequisite for economic resilience, as the health of our commercial enterprises depends on the genetic and species diversity that underpins robust ecosystems. We see the drivers of this degradation manifest through land use changes, overexploitation of biological resources, climate change, pollution, and the spread of invasive species. When we consider the systemic nature of these risks, we must look beyond individual corporate operations and view the global supply chain as a complex, vulnerable web of dependencies. For instance, agricultural outputs are highly sensitive to pollinator health and soil microbiome integrity, meaning that specific biodiversity loss directly impacts food security and commodity price stability. When ecosystems reach a tipping point and cease to provide their regulating or provisioning services, the resulting operational shock can trigger cascading failures across sectors that rely on these steady inputs. Integrating nature-related impacts into your risk management framework requires moving beyond the traditional climate-centric view to acknowledge that climate change and biodiversity loss are mutually reinforcing. If we consider the corporate balance sheet, assets located in ecologically vulnerable regions face heightened exposure to physical decline, while businesses reliant on biodiversity for operational inputs face significant transition risk as regulations and consumer preferences shift towards sustainable sourcing. Companies that fail to evaluate these natural dependencies risk encountering significant stranded asset exposure, similar to carbon-intensive projects that become unviable in a decarbonizing economy. The urgency of this evaluation stems from the fact that nature-related risks are often nonlinear and difficult to value using standard actuarial models developed for more stable environments. By mapping your organizational dependencies against the degradation of specific ecosystem services, you can identify where your exposure is highest and begin the necessary process of mitigation and disclosure. This analytical rigor ensures that you are not just managing surface-level climate outcomes, but are proactively protecting the foundational biological wealth upon which all long-term profitability depends. I will see you in the next section. Welcome to this discussion on the integration of sustainability within corporate and institutional frameworks. In this session, we will explore how organizations embed climate objectives into their core governance and operational structures. When we talk about corporate integration, we are not simply discussing an add-on or a peripheral policy document, but rather the structural re-engineering of how a firm operates. For a board of directors, this means that climate-related risks must be elevated to the same level of scrutiny as financial risks or operational hazards. It requires the establishment of formal oversight mechanisms where directors actively review sustainability metrics as a permanent agenda item. This duty of oversight implies that the board must possess or acquire the technical literacy to challenge management on the trajectory of carbon emissions or the resilience of the supply chain. If the board does not understand the underlying climate data, they cannot effectively govern the fiduciary interests of the firm in a transitioning economy. This shift involves moving away from silos where sustainability is a public relations function and toward a model where it informs capital expenditure, risk appetite, and strategic planning. One of the most potent levers for ensuring this cultural and strategic alignment is the direct linkage of executive compensation to sustainability performance. By tied to KPIs mechanisms, organizations ensure that leadership teams are financially motivated to meet specific environmental milestones. These milestones often include reductions in Scope 1 and 2 emissions, the successful decommissioning of legacy fossil fuel-dependent assets, or the achievement of specific ESG rating improvements. The complexity here lies in setting meaningful targets that are sufficiently ambitious to require genuine operational change rather than simple administrative adjustments. If these metrics remain purely aspirational or easily attainable through offsets, the integration remains superficial and vulnerable to accusations of greenwashing. Consequently, the board must ensure that the methodologies used to calculate these incentives are robust, auditable, and transparent to the broader stakeholder base. Alignment with planetary boundaries necessitates that corporate strategy considers the limits within which the environment can continue to support economic activity. This requires integrating long-term climate scenarios into financial modeling to determine the ongoing viability of existing business models. Institutional investors, acting as stewards of capital, play a critical role here by exerting pressure on their investees to formalize these governance structures. This is where voluntary private sector coalitions provide the necessary guidance for harmonizing industry standards across global portfolios. Initiatives such as the United Nations Principles for Responsible Investment have become essential frameworks for institutional asset managers to communicate their commitment to integrate environmental, social, and governance issues into investment analysis and decision-making processes. These principles help investors move beyond short-term profit maximization toward a more sustainable long-term value creation model. In the banking sector, the United Nations Environment Programme Finance Initiative Principles for Responsible Banking offer a similar roadmap for aligning institutional activities with societal goals. These principles encourage banks to demonstrate that their strategies are aligned with the ambitions expressed in the Sustainable Development Goals and the Paris Agreement. By adopting these standards, financial institutions are essentially committing to a transparent disclosure process that exposes their financed emissions and their progress toward a net zero trajectory. The goal is to move from a defensive risk management posture to an offensive strategy that actively directs capital towards sustainable infrastructure and transition technologies. When banks harmonize their lending practices with these scientific thresholds, they contribute to the global systemic shift required to stabilize the climate. Ultimately, institutional stewardship acts as a catalyst, compelling the entire corporate landscape to treat environmental constraints as fundamental business parameters. See you in the next lecture. Welcome back. In this lesson, we will examine the mechanisms behind greenwashing and how these deceptive practices manifest within corporate disclosures and financial markets. To identify greenwashing, we must first recognize that it often operates through the selective disclosure of positive environmental metrics, while simultaneously omitting negative impacts. When a corporation highlights its renewable energy investments in a glossy report but remains silent about its continued expansion of fossil fuel exploration, they are effectively curating a narrative that hides the truth. This is frequently coupled with the use of vague language such as eco-friendly, green, or sustainable, which lack any standardized legal definition. If a financial product is marketed as being fully aligned with climate targets, yet it invests in companies without a credible transition path, we are looking at a classic case of mislabeled financial offerings. This behavior creates a facade of progress that misleads investors who genuinely seek to reallocate capital towards sustainable ends. By learning to strip away these layers of marketing, you gain the ability to critically assess whether a company's actions are backed by granular, verifiable data. The concept of greenwashing serves as a related, yet distinct, challenge where firms communicate goals that are aspirational rather than strategic. Unlike deliberate deception, greenwashing involves announcing long-term net zero commitments that lack interim milestones, scientific baselines, or a clear investment roadmap. For instance, a firm might claim it will achieve carbon neutrality by 2050 without explaining how the necessary technological or operational changes will be financed. From a risk management perspective, these unsubstantiated claims constitute a significant liability, as they expose the institution to future litigation when the inevitable gap between rhetoric and reality appears. Regulators such as the SEC and the European Securities and Markets Authority are increasingly viewing these gaps as material misstatements. Discerning between a legitimate, evidence-based transition plan and a purely performative one is essential for any sustainability professional aiming to prevent catastrophic reputational erosion. Regulatory bodies are responding to these market distortions by tightening the requirements for ESG disclosures and product classification. We are seeing a shift toward mandatory audit-ready reporting where companies must substantiate their environmental claims with evidence that can be stress-tested against climate scenarios. This scrutiny effectively raises the cost of greenwashing, as the legal ramifications, including hefty fines and mandated restatements, can far outweigh the temporary marketing benefits. Furthermore, the rise of green taxonomies provides a structured framework that defines which economic activities are truly sustainable, making it harder for firms to arbitrarily label assets. When analyzing an organization's claims, you should strictly look for alignment with these emerging technical standards rather than the sentiment carried in their public relations materials. A scientifically grounded approach requires you to look beyond the branding to verify whether the underlying financial flows lead to tangible reductions in greenhouse gas emissions. Understanding these deceptive tactics is vital for protecting your organization's credibility. See you in our next session. Welcome to the session on the transition to a circular economy. We will explore the fundamental shift from linear consumption to restorative industrial systems. The traditional economic model, often described as take-make-waste, functions on the assumption of infinite resource availability and unlimited capacity for waste absorption. We extract raw materials, process them into products with often limited lifespans, and ultimately discard them as externalities. This extraction-heavy dependency exposes firms to volatile commodity markets and significant regulatory risks related to waste management. In contrast, the circular economy is an industrial system designed to be restorative and regenerative by intention. It fundamentally alters how we conceive of value, moving away from volume-based growth models towards service-based or product life extension models. By decoupling economic activity from the consumption of finite resources, corporations can mitigate supply chain disruptions. At the core of this transition are distinct design principles that prioritize the elimination of waste at the conceptual stage. When a product is designed, the engineer must now account for the end-of-use phase with the same rigor applied to manufacturing specifications. This involves selecting materials that are easily separable, non-toxic, and infinitely recyclable without losing structural integrity. We see this manifested in modular product architecture, where individual components can be replaced or upgraded rather than forcing a full replacement of the entire unit. Furthermore, resource efficiency improvements move beyond mere optimization of production lines into the realm of closed-loop material flows. Rather than viewing a byproduct of one process as trash, firms increasingly treat it as a feedstock for another, effectively internalizing what were previously considered bottom-line losses. The shift toward these practices is driven by a combination of business model innovation and mounting regulatory pressures. Corporations are increasingly adopting product as a service models, where the manufacturer retains ownership and the customer pays for the utility provided by the asset. This alignment of incentives encourages manufacturers to create long-lasting, durable products rather than items designed for rapid obsolescence, as every repair or replacement cost impacts the company's own balance sheet. Furthermore, the regulatory landscape is rapidly evolving to penalize linear waste patterns through extended producer responsibility schemes and strict landfill diversion mandates. These policies force companies to account for the environmental liabilities associated with their products long after the point of sale. By proactively mapping these supply chains, firms can uncover novel commercial opportunities that were previously obscured by a failure to account for total lifecycle costs. From a risk management perspective, the circular economy is an essential strategy for insulating a portfolio against the vagaries of raw material markets. Consider the electronics industry, where reliance on critical minerals makes supply chains highly sensitive to geopolitical instability and environmental regulations in the extraction sector. A company with a robust recovery and refurbishment program effectively creates its own, more stable secondary source of base materials. This is not just an environmental initiative. It is a structural hedge against physical and policy-related transition risks. When you analyze a company's sustainability report, pay close attention to their transition plans regarding material intensity and recovered content. Companies that have successfully integrated circularity into their core operations are often better positioned to handle future constraints on natural capital. I will see you in the next session. Welcome to our exploration of climate risk, where we establish the necessary mental models to navigate this complex landscape. This chapter serves as your primary bridge between theoretical climate science and the practical day-to-day discipline of institutional risk management. In this course, we prioritize clarity over density to ensure you pass the GARP SCR exam with confidence. You will learn to map ambiguous environmental phenomena into the structured, rigorous taxonomies that financial regulators and institutions now mandate. We bypass the peripheral noise, focusing strictly on the mechanisms that impact your balance sheet and your career progression in professional finance. Climate risk is not an exotic new category of danger, but rather a set of multipliers that exacerbate the traditional risk pillars you already know. When we look at credit risk, we are no longer just considering the borrower's historical behavior and macroeconomic conditions, but also their vulnerability to sudden shifts in asset valuation due to physical climate events. Similarly, market risk is no longer bounded by historical volatility data because climate change introduces nonlinear shocks that standard models fail to capture. Operational risk expands to include supply chain disruptions from extreme weather, while liquidity risk may spike when markets suddenly reprice long-term assets once deemed safe. Viewing climate through the lens of established risk taxonomies is the only way to integrate these threats into existing enterprise frameworks effectively. Understanding the transmission channels is critical for any risk professional, as these paths explain how macro-level shifts become micro-level losses. Think of the transmission channel as the conduit through which a climate event, whether physical, like a flood, or transitional, like a carbon tax, moves from the environment into the financial statements of a counterparty. A physical shock can directly impair the debt service capacity of a corporate borrower by destroying physical capital, while a policy shift can lead to stranded assets that once counted as collateral. For banks, this triggers a cascade of potential credit defaults. And for insurance firms, it generates an unprecedented volume of underwriting claims that may exceed historical expectations. These channels are the primary site of inquiry for financial regulators because they are where individual institution-level stress begins to threaten broader system stability. We will move through these concepts systematically, ensuring you have the vocabulary to identify, measure, and explain these risks to your stakeholders. This approach ensures you are prepared not just to pass an exam, but to speak the language of governance required in today's sustainable finance environment. See you in our next session. Welcome back to our exploration of climate risk assessment. Today, we address the identification and financial quantification of acute physical risks. Acute physical risks represent discrete, event-driven shocks that manifest through extreme weather phenomena such as tropical cyclones, severe flooding, wildfires, and convective storms. Unlike chronic changes that alter long-term averages, these events are characteristically binary in nature, occurring at a specific point in time with immediate, often catastrophic consequences. The central challenge for a risk manager lies in the fact that historical climate data is no longer a reliable predictor of future frequency or severity. We are witnessing an environment where atmospheric warming increases the energy available to storm systems, leading to more intense precipitation and higher wind speeds. Consequently, your assessment models must shift from a reliance on backwards-looking actuarial tables toward forward-looking probabilistic simulations that account for nonlinear climate dynamics. When we speak of financial quantification, the first order of concern is the direct destruction of capital assets, such as physical infrastructure, manufacturing plants, or agricultural property. However, the balance sheet impact rarely ends with the immediate write-down of these tangible assets, as acute events typically trigger cascading consequences throughout a firm's operational ecosystem. Supply chain disruptions serve as a prime example, where a localized flooding event in a key manufacturing hub can cause a global halt in production, resulting in substantial business interruption losses. These secondary exposures often exceed the value of the direct asset damage, creating significant volatility in revenue streams that must be modeled with precision. You need to identify where your critical dependencies reside geographically and correlate those locations with high-risk hazard zones. Quantifying these risks requires the integration of advanced spatial data with sophisticated climate hazard models that account for current geophysical realities. Traditional insurance models often treat these events as independent variables, but we must integrate granular geolocational data to understand how climate change alters the baseline risk profile of specific coordinates. This necessitates the use of forward-looking hazard modeling, which applies various climate change scenarios to localized geography, allowing us to estimate the projected increase in event probability over the lifetime of an asset. For a bridge or a coastal facility designed to last 40 years, a stagnant baseline is insufficient because it ignores the accelerating thermal trends we discussed in earlier modules. Effective risk management therefore requires adjusting historical loss data based on current warming trends, forcing us to incorporate a climate-adjusted view of extreme event distribution. Beyond the immediate ledger entries, localized macroeconomic distress often follows large-scale acute weather events, creating further systemic complications for institutional investors. A major hurricane or wildfire can lead to a local exodus of labor, a decline in tax revenue, and a broader deterioration of real estate values in the affected municipalities. Financial institutions exposed to regional mortgages or municipal bonds must assess how these disaster-driven externalities influence their credit risk assessments. If your portfolio is heavily skewed toward assets in high-risk zones, you are effectively underwriting climate volatility without a clear understanding of the tail risk distribution. By systematically quantifying these impacts, you provide the necessary visibility for the board to decide whether to transfer this risk, mitigate it through hardening, or move the exposure elsewhere. See you in the next session. Welcome back. Today, we turn our attention to chronic physical risks, which represent the slow-moving, long-term shifts in our climate baseline that fundamentally reshape economic landscapes. When we discuss physical climate risk, it is common to fixate on the catastrophic events that dominate news cycles, such as hurricanes or wildfires. However, from a risk management perspective, the silent, cumulative damage of chronic risks often poses a more profound threat to long-term solvency and asset stability. These risks are characterized by gradual, persistent changes in environmental conditions, such as rising mean temperatures, permanent sea level rise, and the slow encroachment of desertification. Unlike acute events, which allow for a clear recovery timeline, chronic risks create a structural alteration in the environment that rarely reverts. For an institution underwriting a 30-year mortgage or assessing long-term corporate sovereign debt, these shifts effectively rewrite the foundational assumptions of risk and return. Consider the economic implications of rising mean temperatures on commercial operations. As baseline temperatures increase, the energy demand for cooling systems rises proportionally. creating a permanent increase in operational expenditure for businesses located in affected regions. This is not merely a seasonal fluctuation, but a systemic rise in baseline costs that erodes profit margins over time. When companies or municipal entities fail to account for this permanent shift in operational overhead, the resulting squeeze on cash flow can lead to a credit rating downgrade. Furthermore, investors must recognize that such costs are rarely transitory. They are indicative of a permanent alteration in the geographic viability of certain business models. Consequently, capital allocation strategies must evolve to weigh the efficacy of existing cooling infrastructure against the projected cost of cooling in a warming world. Water scarcity and the associated strain on regional infrastructure present another critical facet of chronic risk. As changing precipitation patterns and glacial melt led to persistent water stress, industries that rely heavily on water availability for production or cooling face significant operational constraints. In agricultural sectors, this manifests as a steady decline in crop yields, which directly impacts the credit quality of agribusinesses and the stability of food supply chains. Regional infrastructure, including water treatment facilities and transport networks, may also suffer from premature degradation as they fail to function within the climate parameters for which they were originally designed. Because these risks accumulate over decades, there is a dangerous tendency to treat them as distant problems, yet they represent a current, tangible impairment to the utility and valuation of fixed assets today. Sea level rise serves as a primary example of how chronic physical risk dictates the longevity of asset values. As coastal water levels persistently climb, properties that were historically located on stable dry ground may experience increased susceptibility to tidal flooding and saltwater intrusion. This process does not occur in a vacuum. It impacts the liquidity of real estate markets, insurance premiums, and the underlying collateral security of bank portfolios. If a lender bases an underwriting model on historical flood frequency without integrating the projected trajectory of sea level rise, the risk is fundamentally mispriced. Over time, the permanent loss of land utility or the insurmountable cost of engineering defenses will inevitably lead to a situation where the asset valuation must be written down. This necessitates a more rigorous, forward-looking integration of climate data into the standard underwriting criteria for all geographic regions identified as high risk. Effective risk management requires us to shift from reactive mitigation strategies to proactive predictive modeling. By isolating the impact of these variables from the broader market noise, we can more accurately assess the resilience of a portfolio or a corporate entity. This involves analyzing how long-term environmental trends correlate with the operational and financial endurance of the underlying assets. We are looking for those structural weaknesses that, while quiet today, will compound over the life of a credit instrument. Ultimately, recognizing chronic physical risk is about acknowledging that the baseline environment we operate in is no longer stationary, and our financial models must adapt to this new, evolving reality. See you in the next lecture. Welcome back. Today we address the critical components of transition policy risk and its impact on modern financial portfolios. Transition policy risk represents the financial uncertainty associated with the shift toward a low-carbon economy through regulatory and legislative channels. When governments introduce rapid shifts in climate policy, they create sudden compliance burdens that fundamentally alter the profitability of existing business models. These shifts often manifest as tightened building codes, mandated improvements in industrial energy efficiency, or strict renewable energy standards. For a firm operating in a high-carbon sector, these mandates act as a financial constraint that forces unplanned capital expenditures. Companies must weigh the cost of immediate retrofitting against the risk of facing punitive taxes or market exclusion. As these policies tighten, the cost of carbon becomes a primary driver of operational expenses rather than a marginal consideration. Financial professionals must look beyond current balance sheets to see how these policy pressures erode the future discounted cash flows of high-carbon assets. Failure to internalize these costs often leads to a mispricing of credit risk and equity valuations. One of the most profound mechanisms in this risk landscape is the implementation of carbon border adjustment mechanisms and localized carbon taxation policies. These interventions are designed to protect domestic industries while simultaneously pressuring trading partners to accelerate their own decarbonization timelines. From a risk management perspective, these mechanisms introduce significant volatility into global supply chains and cross-border trade costs. If a manufacturing firm relies on international inputs produced in jurisdictions with weak emission standards, the introduction of a carbon border tax will instantaneously increase their landed costs. This is not merely a theoretical exercise. It creates a direct hit to margins that may be difficult to pass on to consumers in competitive markets. Furthermore, companies often face legal actions that act as an enforcement layer for these policy shifts, creating a feedback loop between regulation and litigation. We see an increasing trend where stakeholders utilize the regulatory framework to hold firms accountable for failing to align with climate objectives. This convergence of policy, carbon pricing, and litigation is what we define as the core of transition policy risk for the SCR candidate. The concept of stranded assets is inextricably linked to these rapid legislative shifts that render legacy infrastructure economically unviable. When a government mandates a ban on fossil fuel-reliant technologies or accelerates the phase-out of coal-fired generation, the remaining book value of these assets faces sudden impairment. Investors often assume that an asset will be productive until the end of its physical lifespan, but policy risk introduces a shorter, artificial economic lifespan. If a utility plant is forced to shut down 10 years earlier than planned due to new emission standards, the unamortized capital investment must be written off immediately. This scenario is particularly dangerous for firms that have loaded their balance sheets with debt based on projected cash flows from those specific assets. We must analyze these risks by stress testing the resilience of firms against different policy implementation speeds. Those that rely on high-carbon, long-lived capital equipment are inherently more sensitive to these policy shocks than service-oriented businesses. Understanding this dynamic is crucial for correctly assessing the solvency and long-term viability of corporate entities in a changing regulatory landscape. We will see how these factors integrate into wider risk models in the next segment. Welcome to our focus on market and technological shifts, where we examine how emerging innovations and changing consumer behaviors drive transition risk for established business models. In this chapter, we will unpack the mechanics of transition risk, specifically focusing on how disruptive technological innovations and shifting market preferences fundamentally alter the risk profile of carbon-intensive firms. You will learn to navigate the complexities of cost deflation in clean energy, the rapid expansion of electric mobility, and the strategic implications of energy storage advancements. By understanding these dynamics, you will be better equipped to evaluate how firms that fail to adapt are increasingly exposed to significant financial erosion. This curriculum is meticulously designed to provide you with a rigorous, evidence-based understanding of the SCR exam requirements, ensuring you master the intersection of finance and sustainability. When we discuss market and technological shifts, we are essentially looking at the speed and magnitude of capital transition away from high-carbon assets. Consider the precipitous decline in the levelized cost of energy for solar and wind power, which has fundamentally changed the economics of utility-scale energy production. As these technologies reach and exceed grid parity, legacy coal and gas-fired plants increasingly function as suboptimal investments that struggle to compete on a purely operational basis. This shift is not merely a matter of environmental preference, but a direct result of capital efficiency and superior technological performance. When a firm relies on an aging, high-emission asset base in a market where renewable alternatives offer higher reliability at lower marginal costs, they face a classic case of technological displacement. This disruption extends beyond the energy sector and into mobility, where electric vehicles are rapidly eroding the manufacturing relevance of internal combustion engines. The rapid cost deflation in lithium-ion battery technology serves as a primary driver, triggering a sequence of events where traditional automotive OEMs are forced into expensive, capital-intensive transitions. Market preferences are shifting in lockstep as consumers, spurred by both regulatory incentives and lower total cost of ownership, move away from fossil fuel-dependent vehicles. Consequently, corporations that do not pivot their research and development portfolios toward these emerging technologies inevitably see their market share decline. This is the essence of transition risk: the erosion of revenue due to an inability to match the changing technological landscape of the broader market. Beyond technological shifts, we must analyze the influence of changing stakeholder expectations, which act as a powerful catalyst for corporate change. Institutional investors are no longer viewing carbon exposure as an externality, but as a core indicator of long-term operational risk and potential bankruptcy. We see this manifested in corporate procurement preferences, where major retailers and tech firms mandate that their entire supply chains adhere to strict decarbonization pathways. When a company cannot demonstrate a transition strategy, they find themselves penalized through higher costs of capital and restricted access to debt markets. This creates a feedback loop where the cost of borrowing for carbon-intensive brands rises, further limiting their capacity to innovate and invest in the very technologies needed for survival. We also see the impact of these shifts in the valuation of intangible assets such as brand equity and corporate reputation. Consumers are increasingly using their purchasing power to signal preferences for companies that align with climate-conscious values and net zero commitments. Brands that are perceived as laggards in the transition are frequently met with negative sentiment, which translates directly into volatility and potential revenue leakage. When a company's primary product offering is perceived as being on the wrong side of the technological and market transition, the investor base begins to discount future cash flows. This is a crucial takeaway for our exam preparation. Transition risk is a multifaceted phenomenon where market sentiment, consumer demand, and technological innovation converge to penalize carbon-heavy firms. Effectively managing these risks requires a sophisticated integration of forward-looking analysis into the firm's enterprise risk management frameworks. It is not enough to look at historical data. One must monitor the inflection points in battery chemistry, renewable energy capacity expansion, and shifting regulatory policy that could trigger rapid capital shifts. By understanding the velocity of these market and technological shifts, an organization can proactively manage its asset portfolio and prevent the realization of trapped value. As you prepare for the exam, keep in mind how these dynamics translate into quantitative impacts on a firm's balance sheet and operational efficiency. The ability to identify these signals is essential for any practitioner involved in sustainability and climate risk assessment. I will see you in our next technical deep dive. Welcome back. In this session, we will examine the intersection of legal climate liability and the financial reality of stranded assets within carbon-intensive industries. Climate liability risk represents the potential for financial loss stemming from legal actions directed at organizations perceived to be responsible for climate change impacts. These litigations are increasingly sophisticated, focusing on three primary pillars: claims for physical damages, allegations of failure to disclose material climate-related risks, and charges of misleading green claims. When a corporation faces a lawsuit for environmental degradation, it is not merely a reputational concern, but a direct balance sheet threat. Plaintiffs, ranging from municipalities to activist groups, utilize established legal precedents to argue that companies knowingly contributed to climate instability or obfuscated transition risks from shareholders. If a court determines that an entity failed in its duty of care or breached disclosure obligations, the resulting settlements or judgments can impair capital structures significantly. Consequently, liability risk translates directly into institutional financial risk, impacting the cost of capital and insurance premiums for the exposed firm. The concept of stranded assets sits firmly at the heart of the transition risk conversation, describing investments that suffer from unanticipated or premature write-downs, devaluations, or full conversion to liabilities. These assets lose their economic viability before the end of their expected useful life because the surrounding economic, regulatory, or social system shifts away from carbon dependence. Consider a coal-fired power plant that was projected to operate for 40 years but becomes commercially unviable after 15 due to the introduction of a high carbon tax or a surge in cheap renewable energy competition. The unrecovered capital expenditure remaining on the balance sheet represents the stranded value, which must be impaired or written off, potentially triggering a broader reassessment of the company's enterprise value. This phenomenon is not limited to physical infrastructure. It extends to proved fossil fuel reserves that may never be extracted under a net zero trajectory, effectively turning valuable balance sheet assets into atmospheric liabilities. We must also broaden our view to include stranded human capital, which refers to the workforce skills and livelihoods tethered to declining carbon-heavy industries that lack the infrastructure for a just transition. If an entire regional economy is built around a single fossil fuel sector, the rapid obsolescence of those assets leaves not just the machinery abandoned, but the workforce without a clear path toward new employment. Just transition principles emphasize that the phase-out of high-emission activities must account for these social externalities, ensuring that economic shifts do not exacerbate inequality or regional decay. From an institutional finance perspective, the failure to prepare for this transition creates a systemic contagion risk. When diversified financial institutions hold large exposures to industries with high densities of potentially stranded assets, a sudden sectoral collapse can lead to rapid capital flight and market volatility, impacting the broader stability of the financial system. Effective identification and management of these risks require a systematic mapping of an organization's portfolio against various transition pathways. Analysts should examine the carbon lock-in effect, where long-lived assets force a company to continue high-emission pathways to maintain profitability, thereby increasing the severity of a potential later write-down. By integrating these considerations into enterprise risk management, firms can begin to measure the loss given default or impairment risk associated with individual asset classes. This involves rigorous stress testing against scenarios where carbon pricing or policy shifts accelerate the abandonment of specific energy sources. The goal is not merely to divest, but to understand the sensitivity of the entire balance sheet to rapid depreciation, enabling proactive capital reallocation. By recognizing these liabilities early, institutions can better align their strategies with the evolving global regulatory landscape and prevent the catastrophic accounting impacts associated with sudden asset strandedness. I will see you in the next lecture. Welcome to this exploration of the formal architecture governing international climate policy. In this chapter, we will trace the evolution of global agreements while focusing on the mechanisms that underpin current climate risk management. The history of international climate governance is fundamentally rooted in the 1992 United Nations Framework Convention on Climate Change, or UNFCCC. This treaty established the foundational objective of stabilizing greenhouse gas concentrations to prevent dangerous human interference with the climate system. It did not initially contain legally binding emission targets, but it created the framework for subsequent negotiations. The first major milestone following this was the Kyoto Protocol in 1997, which introduced the concept of common but differentiated responsibilities. This meant that developed nations, having contributed the most to historical emissions, took on binding reduction targets first. While the Kyoto Protocol established the mechanics of international emissions trading and clean development mechanisms, its scope was eventually viewed as insufficient for a truly global challenge. The transition from Kyoto to the Copenhagen Accord marked a significant shift in diplomatic strategy. The Copenhagen meetings failed to produce a new successor to the Kyoto Protocol, yet they signaled a pivot toward a more inclusive approach that required participation from both developed and emerging economies. This evolution eventually culminated in the 2015 Paris Agreement, which represents the current gold standard for global climate ambition. Unlike the top-down legal structure of Kyoto, the Paris Agreement utilizes a hybrid model of voluntary national commitments supported by transparent reporting. This shift reflects a pragmatic understanding that global cooperation functions best when it allows for varied economic circumstances while maintaining a shared, rigid, long-term objective. At the center of the Paris Agreement is the mandate to limit the increase in global average temperature to well below 2 degrees Celsius above pre-industrial levels. Furthermore, the members pursue efforts to limit this temperature increase further to 1.5 degrees Celsius, acknowledging that the climate impacts of a 2-degree rise are significantly more damaging than those at 1.5. This target is not merely an aspiration, but a core driver for national policy, corporate regulation, and global capital allocation. To hold governments accountable, the agreement employs a mechanism known as the global stocktake. This process occurs every 5 years to assess collective progress toward the long-term goals and to inform the next round of national ambitions, ensuring that the policy architecture remains dynamic despite being non-binding under international law. The operational success of this architecture relies on the bottom-up nature of the commitments. Each party submits their own plans, known as nationally determined contributions, which detail how they intend to achieve their emission reduction targets. This structure acknowledges the sovereignty of individual nations while creating a system of public transparency that exerts peer pressure on all participants. Because the agreements are essentially collaborative, they rely on the veracity of disclosed data and the consistency of national policies. For professionals, understanding these agreements is essential because they define the transition policy risks that companies face globally. When governments adjust these national plans to meet the Paris goals, they create specific regulatory shifts that directly impact market competition and asset valuations. As we continue our analysis, recognize that these international agreements function as the bedrock for all other climate policy instruments. They dictate the trajectory of carbon pricing, technological subsidies, and the inevitable phase-out of fossil fuel-dependent infrastructure. Without the framework established in Paris, the systematic push toward net zero would lack the legal and normative justification required for large-scale institutional mobilization. We will build on this understanding in subsequent sessions to see how these high-level commitments filter down into specific corporate and financial obligations. By keeping the global mandate in mind, you can better navigate the regulatory complexities that define the current climate risk landscape. I look forward to discussing how these goals manifest in specific national strategies during our next session. Welcome back. In this session, we examine the mechanics of nationally determined contributions as they function under the architecture of the Paris Agreement. The Nationally Determined Contribution, or NDC, serves as the fundamental unit of accountability for countries participating in the Paris Agreement. Each party is required to prepare, communicate, and maintain successive plans that outline their commitments to mitigate greenhouse gas emissions and adapt to climate change. These documents represent a bottom-up approach to international climate policy, ensuring that individual nations retain sovereignty over their specific pathways toward decarbonization. The core requirement is that every subsequent NDC must reflect a progression beyond the previous version, representing the highest possible ambition that a state can manage given its national circumstances. This dynamic feature, known as the ratcheting mechanism, is designed to ensure that global climate action scales over time rather than stagnating at current levels. For those of us analyzing financial risk, these documents provide the most reliable signals for future government policy direction. When a government publishes an updated NDC, it is essentially declaring its intent to modify the regulatory landscape of its domestic economy. Understanding these documents is necessary to anticipate how a national government might reallocate capital, change carbon pricing regimes, or impose new emissions mandates upon private industry. Translating these high-level national targets into actual economic change requires a granular approach that touches upon every critical sector of the economy. When a country commits to a specific reduction target in its NDC, that target must be operationalized through domestic statutory mandates that force change upon the power generation, heavy industry, transport, and real estate sectors. In the power sector, we frequently see these commitments manifest as legislated phase-outs of coal-fired generation or mandates for the integration of intermittent renewable sources. Heavy industry faces similar pressure, as NDCs often lead to the implementation of sector-specific subsidies that reward the adoption of low-carbon technologies like green hydrogen or carbon capture and storage. The transportation sector must grapple with shifts toward electrification, usually supported by government-funded infrastructure projects and procurement standards that favor zero-emission fleets. Meanwhile, the real estate sector feels the impact through tightened building codes, which mandate higher energy efficiency standards for new construction and significant retrofitting requirements for older assets. If you are assessing the credit risk of a corporation operating within these sectors, you cannot ignore the domestic legislation that stems directly from the national commitment. The NDC acts as a lead indicator for where subsidies will flow and where regulatory costs will be incurred, forcing corporations to align their long-term capital expenditure plans with these broad national trajectories. The complexity of these instruments arises from the variance in how countries choose to structure their internal reporting and enforcement mechanisms. Some nations opt for economy-wide targets that imply a uniform push across all sectors, while others produce highly detailed plans that specify emission ceilings for manufacturing or agriculture. As an analyst, you must distinguish between targets that are unconditional, meaning they will be pursued regardless of external circumstances, and conditional targets that rely on international support, technology transfer, or climate financing. Understanding the difference between these types is vital when constructing risk models, as a conditional target has a significantly higher probability of failure if international support metrics do not materialize as expected. Furthermore, the effectiveness of an NDC is often tied to the legal character of its domestic implementation. A plan enshrined in primary legislation carries significantly more weight than a statement of intent issued by a ministry. We monitor these legal frameworks because they dictate the materiality of transition risk for institutional portfolios. When a nation strengthens its NDC, it effectively shortens the runway for industries dependent on carbon-intensive processes to adjust their business models. Failing to account for these policy shifts leaves a portfolio vulnerable to sudden stranding of assets or regulatory shocks. See you in the next lecture. Welcome back. We are now turning our attention to the policy levers governments use to manage emissions, specifically focusing on carbon taxing mechanisms. In economic theory, the primary justification for a carbon tax is the internalization of environmental externalities. When a firm burns fossil fuels, the resulting greenhouse gas emissions impose costs on society in the form of climate change. Yet these costs are rarely reflected in the market price of the fuel. By imposing a direct price on the carbon content of energy sources, governments intend to shift the supply curve to reflect the true social cost of consumption. This effectively creates a price signal that encourages energy efficiency and the adoption of low-carbon technologies. The underlying logic assumes that if we make the activity expensive, market participants will naturally find the most cost-effective ways to reduce their output. This approach is generally preferred by economists because it provides price certainty to investors, unlike quantity-based mechanisms that leave the price to fluctuate with market demand. Designing a functional carbon tax requires a clear determination of the point of regulation, which is often dictated by administrative feasibility. Most jurisdictions choose to apply the tax upstream, at the point where fuel enters the economy, such as at refineries or border import points, rather than downstream at the point of combustion. This choice minimizes the number of entities that must be monitored, significantly reducing the costs of oversight and compliance. Once the point of regulation is set, the government must establish a price escalation path to provide long-term certainty. Without a predictable increase in tax rates over time, businesses might postpone capital expenditures on green technology, expecting a policy reversal or stagnation. A credible, transparent roadmap allows capital markets to factor future carbon costs into asset valuations today, which is essential for long-term strategic planning. A significant concern for policymakers implementing these taxes is carbon leakage, which occurs when production shifts to jurisdictions with laxer regulations. To mitigate this risk, countries often implement carbon border adjustment mechanisms, which impose a fee on imports equal to the carbon price producers would have paid domestically. This levels the playing field for energy-intensive, trade-exposed industries such as steel or cement manufacturing, which would otherwise be at a competitive disadvantage. However, these adjustments are complex to enforce and must be carefully structured to remain compliant with international trade agreements. Without these protections, domestic industry competitiveness suffers while global emissions remain largely unchanged, a phenomenon often referred to as simply exporting emissions rather than reducing them. The final component of tax design is revenue recycling, which acts as a crucial lever for maintaining political and economic stability. Governments often face the dilemma of how to handle the substantial revenue generated by carbon levies. One approach is revenue-neutral recycling, where the funds are returned directly to households through dividends, effectively offsetting the increased cost of energy for consumers. Alternatively, the revenue can be directed towards subsidizing green infrastructure, funding research and development for emerging technologies, or lowering other distortionary taxes, such as corporate income taxes. Regardless of the chosen strategy, the macroeconomic impact depends heavily on how these revenues are deployed. A well-designed tax that recycles revenue efficiently can mitigate the regressive nature of energy price increases while simultaneously accelerating the transition to a low-carbon economy. See you in the next lecture. Welcome back. Today, we are delving into cap and trade systems as a primary market-based mechanism for carbon pricing. At the core of an emissions trading system lies the principle of setting a rigid, aggregate statutory emissions cap that decreases over time. By defining a finite pool of emission allowances, the regulator effectively enforces a scarcity-based value on carbon output, which directly incentivizes firms to reduce their internal emissions to avoid purchasing excess permits. When a government or administrative body determines the total allowable quantity of greenhouse gas emissions for a specific sector, it converts these into tradable units where one allowance typically represents the right to emit 1 metric ton of carbon dioxide. The system essentially creates a market where the cost of pollution is internalized into corporate operational budgets, fundamentally shifting decarbonization from a theoretical objective to a concrete financial variable. Achieving this requires careful calibration between the total volume of allowances issued and the desired pace of industrial transition across the economy. Allowance allocation methodologies often represent a delicate balance between fiscal policy and political pragmatism, typically split between auctions and free grandfathering. Auctions serve as the most efficient method for initial distribution, as they ensure price discovery occurs naturally based on market supply and demand, while generating government revenue that can be reinvested into green infrastructure. Conversely, free allocation, often termed grandfathering, is frequently used to mitigate the risk of carbon leakage, where firms might otherwise relocate production to jurisdictions with less stringent environmental regulations. This free distribution is usually based on historical emission profiles or sector-specific benchmarks, which can sometimes blunt the price signal if not phased out or tightened over time. Regulators must manage the transition from free allocation to competitive bidding to ensure the domestic industry remains competitive while still facing the necessary pressure to invest in low-carbon technologies. Market stability and price volatility are persistent challenges within cap and trade systems, necessitating the implementation of mechanisms like market stability reserves. Because these markets are sensitive to exogenous shocks, such as sudden shifts in industrial output or major policy oscillations, the price of permits can fluctuate wildly, leading to uncertainty for long-term corporate decarbonization planning. A market stability reserve acts as a buffer by automatically absorbing or releasing allowances based on predefined quantities in circulation, thereby preventing price crashes or extreme spikes. In the European Union emissions trading system, for example, the reserve serves as a feedback loop that helps maintain the system's integrity by adjusting the supply of allowances in response to surpluses that would otherwise undermine the carbon price. Such mechanisms are vital for ensuring that the market remains a credible and predictable instrument for achieving medium-term climate goals. Integration of offsets and rigorous compliance enforcement remain the final pillars that ensure these systems stay grounded in real emission reductions. Offset mechanisms allow organizations to fulfill a portion of their compliance obligations by funding external projects that sequester or reduce emissions, such as reforestation or renewable energy installations. While these can provide lower-cost compliance alternatives, they inherently introduce risks regarding the additionality and permanence of these external reductions, which is why regulators impose strict criteria for which project types qualify. Compliance is ultimately maintained through transparent monitoring, reporting, and verification protocols where firms must surrender their verified emissions data annually. Failure to surrender sufficient allowances to cover actual emissions results in heavy, non-discretionary financial penalties, ensuring that the market price acts as a binding constraint on corporate operational behavior. I look forward to discussing regional regulatory trends in our next session. Welcome to the chapter on global regulatory trends. Here, we analyze how international standards are shifting from voluntary disclosures toward rigid, legally binding mandates for financial institutions and corporations. If you are serious about passing the SCR exam, you realize that the landscape of climate regulation is not static. It is, in fact, accelerating at an unprecedented pace. This chapter is designed to cut through the noise of shifting policies, providing you with a high-level view of how major jurisdictions are transforming sustainability from a corporate social responsibility initiative into a pillar of prudential supervision. By the end of this journey, you will recognize the underlying patterns of global regulatory convergence, specifically how securities regulators and central banks are aligning their expectations. We don't just memorize current laws as those change. Instead, we learn the mechanisms of policy enforcement that you will encounter on the exam. This preparation is your competitive edge, ensuring you can anticipate how regulatory pressure directly influences enterprise risk management and the bottom line for global firms. In this lesson, we track how sustainability regulations are transitioning from soft law best practices into hard, statutory requirements across major economic blocs. The current trajectory demonstrates a clear shift toward mandatory reporting, where transparency is no longer an option, but a prerequisite for market participation. Securities regulators are increasingly focused on preventing greenwashing by enforcing standardized climate risk disclosures that align with international benchmarks like the TCFD. This means firms can no longer rely on vague qualitative statements. They must provide quantitative, decision-useful data that reflects their exposure to physical and transition risks. We see this consolidation of requirements as a move towards harmonization, aimed at reducing the burden of fragmented local standards while simultaneously increasing the quality of climate-related information available to investors. This regulatory tightening is not limited to capital markets. It is equally prevalent in the due diligence requirements imposed on the broader supply chain. The scope of these regulations often includes corporate sustainability due diligence directives, which compel organizations to take responsibility for environmental impacts deep within their value chains. It is not sufficient to manage risk within your own four walls anymore, as regulators are demanding visibility into the total footprint of an entity's business relationships. This trend effectively forces companies to treat environmental impacts as a liability that, if mismanaged, can trigger significant legal and structural consequences. We are seeing laws that introduce mandatory audits, public reporting requirements for Scope 3 emissions, and strict environmental compliance expectations for suppliers regardless of their headquarters location. This approach creates a cascading effect where the largest financial actors impose their own regulatory-driven standards on smaller entities throughout the global economy. By understanding this pressure, you can see why climate risk reporting is rapidly becoming a core component of fundamental corporate governance. Simultaneously, central banks and financial watchdogs are integrating climate change into their macro-prudential supervision mandates to protect systemic financial stability. The thesis here is straightforward. Climate-related risks, such as extreme weather events or structural shifts in the energy sector, represent a material threat to the balance sheets of the banks they regulate. Consequently, supervisory authorities are now embedding climate risk assessments directly into banking licensing requirements and ongoing monitoring protocols. Banks are being prompted to show how they account for long-term transition risk in their loan portfolios and how they might withstand potential climate-driven shocks. These supervisors are looking for evidence that climate risks are integrated into the existing risk appetite framework of the institution. This is not purely about insurance or lending. It is about ensuring that the entire financial system can survive the transition to a low-carbon economy without experiencing a collapse in asset valuations. These systemic financial stability assessments represent the cutting edge of prudential regulation and highlight why the regulator's role has shifted from passive observer to active engine of climate policy. When a central bank performs a climate stress test, they're essentially modeling how different economic outcomes, such as a sudden rise in carbon prices or a collapse in fossil fuel-dependent asset values, impact the capital ratios of regulated entities. This requires a level of data granularity that many institutions are only just beginning to develop, further demonstrating why your mastery of these metrics is critical for the SCR exam. As we track these trends, you will notice that the objective is not to penalize firms, but to ensure they have the internal processes to measure and mitigate these risks accurately. It is a systematic redesign of risk management where climate science, economic forecasting, and regulatory compliance become inseparable pillars of the modern financial firm. I look forward to our next discussion on these matters. Welcome back. In this lecture, we examine green taxonomies, which provide the essential technical vocabulary required for regulators and investors to define what truly qualifies as an environmentally sustainable economic activity. The primary challenge in sustainable finance has long been the lack of a standardized language, often leading to market fragmentation and the proliferation of greenwashing. Green taxonomies emerge as a solution by creating rigorous, science-based classification systems that allow market participants to identify investments aligned with climate goals. When we talk about these frameworks, we are moving away from vague marketing claims toward granular, data-driven assessments of corporate activities. By establishing objective criteria, these taxonomies serve as the foundation for green bond frameworks and help organizations track capital expenditure with greater precision. This clarity is not merely an administrative exercise, it is a fundamental shift in how capital is allocated across the global economy. As we look at different regional implementations, we see that they act as a bridge between high-level policy targets and localized financial decisions. Understanding these mechanics is essential for anyone preparing for the exam, as these standards underpin most modern sustainable finance regulations. The European Union taxonomy stands out as the most comprehensive example of this classification approach, and it rests on three main pillars that you must understand conceptually. First, an activity must make a substantial contribution to at least one of six environmental objectives, such as climate change mitigation or the circular economy. Second, the activity must satisfy the do no significant harm criteria, which ensures that working toward one environmental goal does not undermine others. This is a critical nuance because it prevents firms from claiming sustainability while simultaneously causing environmental degradation elsewhere in their operations. Third, the enterprise must comply with minimum social safeguards, incorporating international norms on human and labor rights into the environmental assessment. This tripartite structure ensures a holistic view of sustainability rather than a narrow focus on carbon performance alone. If a business activity fails any one of these pillars, it cannot be classified as taxonomy aligned, regardless of how environmentally positive other aspects of the project might look. Beyond the European model, the implementation of regional taxonomies has profound implications for how corporations report their transition plans and capital expenditures. These taxonomies reduce the cost of compliance and increase transparency because they essentially provide a technical recipe for what constitutes a green activity. By standardizing these definitions, regulators are successfully curbing the potential for firms to engage in greenwashing by shifting the debate from subjective interpretations to objective technical thresholds. For instance, in the context of capital expenditure, a company can now clearly tag specific investments as aligned with their local taxonomy, providing a verifiable metric for investors. This granularity also feeds into the broader sustainability reporting landscape, providing the raw data needed for TCFD disclosures and other global reporting requirements. By mapping their operations against these technical criteria, companies can identify not only where they are aligned, but also where they need to invest to meet future sustainability targets. As these standards become more deeply embedded in global financial markets, they serve as the backbone for green bond frameworks and sustainable investment classifications. When a financial entity issues a green bond, the methodology used to define the nature of the underlying assets is almost always informed by these existing taxonomies. This creates a link between technical environmental science and the risk assessment processes required by institutional investors. Investors demand these standards because they mitigate the risk of investing in assets that are incorrectly labeled, which could lead to significant reputational and financial consequences. Furthermore, the interoperability between different regional taxonomies remains a major focus for policymakers who wish to avoid creating new forms of market fragmentation on a global scale. Mastering these frameworks allows you to understand how environmental science is converted into financial information, which is a core requirement for the exam. I will see you in the next lecture. Welcome back to our journey through the GARP SCR curriculum. In this module, we step into the expansive domain of sustainable finance to understand how capital markets drive the transition to a low-carbon economy. Sustainable finance functions as the bridge between global capital allocation and the urgent requirements of climate mitigation and adaptation. At its core, this field involves the process of taking due account of environmental, social, and governance considerations when making investment decisions in the financial sector. We are not merely talking about altruism or corporate social responsibility, but rather a fundamental shift in how markets value risk and opportunity over long-term horizons. Capital markets are the primary machinery for mobilization, as they possess the liquidity and reach required to fund large-scale projects that drive decarbonization. When we analyze this landscape, we must distinguish between different responsible investment modalities that range from simple exclusionary screening to impact-focused thematic investing. Understanding the scale of these sustainable assets is crucial because it provides context for how systemic changes in financial policy ripple through global banking, asset management, and insurance sectors. The market dynamics here are defined by a move toward transparency and the alignment of portfolios with net zero pathways. Institutional participants, such as pension funds, sovereign wealth funds, and large asset managers, are the dominant forces dictating capital demand. These entities are increasingly under pressure from regulators and end investors to demonstrate how their capital allocation frameworks contribute to macroeconomic sustainability objectives. It is a strategic alignment process where the objective is to reduce exposure to carbon-intensive assets while seeking resilience in a changing climate. For instance, consider a major institutional investor reallocating funds away from coal-fired power infrastructure toward renewable energy projects. This is a direct manifestation of market dynamics influenced by policy shifts in investor preference. Such actions force a redistribution of capital that effectively penalizes high-carbon activities while rewarding those that are compatible with a 1.5-degree trajectory. To grasp the full picture, one must recognize that responsible investment is not a monolithic concept, but a spectrum of integration strategies. On one end, we have negative screening, where investors simply avoid specific companies or sectors such as tobacco or oil and gas. On the other end, we have impact investing, which intentionally targets specific, measurable social or environmental outcomes alongside financial returns. The sheer scale of these assets has shifted from a niche concern to a standard requirement for fiduciary duty in many jurisdictions. As policymakers refine their definitions of what constitutes a sustainable economic activity, the reliance on taxonomy-aligned data becomes paramount for market participants to avoid reputational and regulatory hurdles. This entire ecosystem rests on the premise that climate-related risks are fundamentally financial risks that need to be priced into the cost of capital. The role of the banking sector is particularly noteworthy, as they provide the financing, loans, and credit facilities that underwrite the real-world economy. Unlike asset managers, banks are frequently exposed to the transition risks faced by their corporate clients, creating a feedback loop between banking portfolios and climate outcomes. By integrating sustainability criteria into credit underwriting, banks can influence the economic behaviors of their borrowers at a granular level. This is where the long-term macroeconomic perspective becomes vital, as shifting capital towards sustainable development goals requires navigating the complexities of emerging markets and diverse regulatory environments. It requires a sophisticated understanding of how policy targets, such as those embedded in nationally determined contributions, translate into actual project pipelines. The success of this transition depends on whether public policy can de-risk climate-positive projects enough to attract the vast pools of private capital waiting on the sidelines. I look forward to discussing how these theoretical constructs are applied through specific investment strategies in our next session. Welcome back. Today we examine the specific taxonomy of ESG investment strategies that define how institutional capital interacts with sustainability mandates. When we talk about ESG investing strategies, we are essentially looking at a toolkit investors use to translate sustainability preferences into portfolio outcomes. The most foundational approach is negative exclusionary screening, which draws a boundary around certain sectors or business activities that an investor finds unacceptable. This might involve stripping out companies involved in tobacco, armaments, or thermal coal mining from the investment universe. While this strategy is operationally simple to implement, it often results in a tracking error relative to a broad market index because entire sectors are removed regardless of their individual financial strength. It acts as a blunt filter rather than a subtle optimization tool, and its primary purpose is to align the portfolio with the investor's ethical constraints while accepting that you are effectively limiting your opportunity set. If exclusion is the act of removing, then positive best-in-class screening is the act of selecting based on relative performance. Here, an investor does not necessarily boycott an entire industry, but instead ranks companies within their respective peer groups based on ESG performance metrics. The goal is to favor companies that demonstrate management of environmental or social risks superior to their industry averages. This allows for a more diversified portfolio compared to simple exclusions, because you maintain exposure to a sector while tilting your weights toward the leaders. It is a more nuanced strategy that leverages the idea that companies with robust ESG systems are generally better managed and may offer lower long-term risk profiles. Norms-based screening operates by defining a set of minimum standards, often grounded in international conventions like the United Nations Global Compact or the ILO Declaration on Fundamental Principles and Rights at Work. When a portfolio manager employs this strategy, they monitor companies continuously for breaches related to human rights, labor practices, environmental damage, or corruption. Unlike simple exclusion, which is static, norms-based screening involves active monitoring and engagement once a red flag appears. If a company fails to rectify a violation, it is divested until operations align with the predefined universal norms. This approach bridges the gap between active stewardship and passive asset selection. Systematic ESG integration represents a shift where ESG factors are treated as material inputs in the quantitative or fundamental financial valuation model. Instead of relying on a separate score, a credit analyst or portfolio manager builds climate risk or social impact directly into their cash flow projections or cost of capital estimates. For instance, if a company has high exposure to carbon-intensive assets, that risk is factored into the discount rate, effectively lowering the present value of the stock. This is arguably the most sophisticated approach because it moves sustainability from the periphery of moral consideration into the core of investment logic. Integration assumes that climate and social variables have direct, measurable impacts on the long-term risk-adjusted return of an asset. Thematic investing focuses capital on specific trends or goals, such as clean energy production, circular economy infrastructure, or global water scarcity solutions. By directing capital toward these themes, investors aim to capture the growth potential of a transition toward a more sustainable economy. This is often contrasted with impact investing, which explicitly requires an investor to measure and report on the intent to generate a positive, measurable social or environmental impact alongside a financial return. Impact investing is unique because it forces a double objective function, meaning the investor holds the asset accountable for its real-world outcome as much as its financial yield. While thematic investing is often focused on sector growth, impact investing is focused on solving a specific, tangible problem. These strategies are not necessarily mutually exclusive, and many institutional investors employ a combination to satisfy complex mandates. Using a hybrid approach allows an organization to exclude harmful activities, select the best performers in necessary transition industries, and integrate climate risk into their broader financial forecasting. This combination significantly alters the risk-return profile of a portfolio by potentially reducing volatility associated with climate policy shocks and increasing exposure to firms better prepared for a decarbonizing world. Ultimately, these strategies change which companies receive the lowest cost of capital, gradually shifting the corporate incentive structure to favor long-term sustainability markers over short-term financial artifacts. See you in our next session. Welcome to our examination of the green bond market, where we will dissect the structural mechanics and regulatory frameworks that define this asset class. We shall focus on the standardization efforts and the economic dynamics that influence investor behavior in this space. The green bond market has evolved from a niche category into a pillar of sustainable finance, primarily guided by the green bond principles promulgated by the International Capital Market Association. At its core, these principles establish a voluntary process that encourages transparency and integrity in debt financing for environmental objectives. The framework rests upon four essential pillars that dictate how an issuer must behave to maintain market trust. First, the use of proceeds must be explicitly dedicated to eligible green projects, such as renewable energy development, waste management, or energy efficiency retrofits. Second, the issuer must have a clear process for project evaluation and selection, ensuring that the defined criteria align with their overarching sustainability strategy. Third, the management of proceeds requires a degree of financial ring fencing, ensuring that funds are tracked and held in sub-accounts to prevent misuse. Finally, the issuer commits to mandatory annual reporting, which provides investors with visibility into the deployment of funds and the resulting environmental impact. Understanding the economic behavior of these instruments often leads us to the concept of the greenium, which is the pricing advantage an issuer may experience when issuing green bonds compared to traditional vanilla bonds. In a theoretical market, high demand for sustainable assets relative to the supply of green bonds drives the yield down for the issuer, effectively lowering their cost of capital. However, this phenomenon is not always consistent and can depend heavily on market volatility, the credit quality of the issuer, and the specific sector in which the proceeds are deployed. While the greenium creates a financial incentive for companies to seek green labeling, it also requires them to navigate the added administrative costs associated with external reviews. These external reviews, or second-party opinions, provide an independent verification that the bond aligns with the stated environmental goals. This verification process is crucial for mitigating the risk of accusations regarding greenwashing, as it provides a seal of technical competence from third-party experts. The integrity of the market depends largely on the quality of reporting requirements and the transparency of environmental metrics. Issuers are expected to disclose not only the allocation of funds, but also the quantitative environmental impacts, such as avoided carbon emissions or water savings. This reporting cycle is continuous, requiring the issuer to maintain documentation until the proceeds have been fully allocated. When an investor purchases a green bond, they are essentially outsourcing the due diligence of environmental impact to the reporting frameworks the issuer has adopted. If the issuer fails to meet these reporting standards, they risk reputational damage and the loss of access to the segment of the investor base that mandates specific sustainability disclosures. Consequently, the relationship between the issuer and the investor is defined by this ongoing flow of data, which serves as a proxy for the actual physical progress of the underlying projects. We must look at these instruments through a lens of risk management rather than just asset allocation. While the credit risk of a green bond is generally identical to a non-green bond from the same issuer, the non-financial risks are different. Regulatory shifts or failures in meeting sustainability targets can lead to forced divestment by ESG-mandated funds, which introduces a distinct type of liquidity risk. Furthermore, as taxonomies become more rigid, bonds that are currently labeled green may fall out of compliance if the underlying project, such as a large-scale hydro dam or biomass project, is reclassified based on updated scientific consensus regarding environmental impacts. By understanding these mechanics, you will be better equipped to evaluate the long-term viability of green debt within a balanced investment portfolio. I will see you in the next lecture. Welcome back. Today we examine the mechanics and strategic intent behind sustainability-linked loans and bonds. In the landscape of sustainable finance, we encounter a fundamental divergence between use of proceeds instruments, such as standard green bonds, and performance-based instruments. While a green bond earmarks capital for specific projects like wind farms or retrofitted infrastructure, sustainability-linked loans represent a shift toward behavior-based lending. These instruments do not necessarily restrict where the money goes. Instead, they alter the financial terms of the loan based on the borrower's overall corporate sustainability performance. If a borrower achieves predefined sustainability performance targets, they may benefit from a lower interest rate, often referred to as a step-down. Conversely, failing to meet these benchmarks can trigger an increase in the cost of debt, known as a step-up. This creates a direct financial incentive for management to integrate climate considerations into their core operational strategy. The structural integrity of a sustainability-linked loan relies heavily on the definition of key performance indicators and the calibration of sustainability performance targets. These indicators serve as the measurable metrics, such as a reduction in Scope 1 and 2 greenhouse gas emissions or a specific percentage increase in renewable energy sourcing. The challenge for market participants lies in ensuring that these targets are ambitious rather than merely business-as-usual projections. A target that is easily met without significant operational change fails to drive the transition required by stakeholders and regulators. Consequently, lenders must scrutinize the baseline data provided by the borrower to ensure it represents a credible starting point against which future progress can be objectively verified. Regulatory bodies and market associations provide guidelines to prevent greenwashing, which occurs when a borrower claims sustainability improvements that lack substance. The Loan Market Association and the International Capital Market Association have established principles that emphasize the importance of independent, external verification. Without an external audit or a third-party opinion, the market lacks the assurance that targets are being met honestly. These guidelines also require ongoing reporting, ensuring that performance is disclosed transparently over the life of the instrument. If a borrower fails to report or meet the agreed-upon targets, the structural legal mechanics of the loan agreement are activated to adjust the financial terms accordingly. When we analyze the effectiveness of these loans, we must distinguish between the financial materiality and the reputational value of the instrument. For the lender, these loans integrate climate risk directly into the credit assessment process by linking debt service costs to sustainability outcomes. By tying the interest rate to carbon intensity or other ESG metrics, the lender creates a feedback loop that rewards firms making actual progress in their transition journey. This transition is not instantaneous. It requires careful monitoring and a robust legal framework that defines exactly what constitutes a breach of a sustainability covenant. The goal is to move beyond simple compliance and toward a model where sustainability performance is a standard component of institutional credit analysis. The evolution of these instruments reflects a broader maturity in the capital markets, moving away from thematic silos and into general corporate liquidity. Because these loans can be applied to general corporate purposes, they are accessible to a wider array of issuers who may not have enough individual green projects to justify a dedicated green bond issue. However, this flexibility increases the risk if the key performance indicators are poorly chosen or if the targets are too loose. As the market develops, we are seeing a convergence towards standardized definitions that help lenders and investors compare performance across different sectors. This push for standardization is essential to ensure that sustainability-linked debt remains a credible tool for financing the global economic transition. See you in our next exploration of these topics. Welcome back. In this lesson, we explore the evolving retail landscape of consumer-facing sustainable finance products, examining how traditional banking meets environmental objectives. Financial institutions are increasingly pivoting toward retail-facing sustainability products to meet growing demand from individual depositors and borrowers. This shift involves re-engineering core retail offerings like mortgages and auto loans to reflect the environmental profile of the underlying asset. A green mortgage, for instance, typically incentivizes homeowners by providing lower interest rates or reduced fees for properties that satisfy rigorous energy efficiency criteria, such as superior insulation ratings or low-carbon heating systems. Similarly, eco-friendly auto loans target the financing of electric or high-efficiency hybrid vehicles, creating a distinct portfolio segment that aligns retail lending with corporate net zero targets. These products require careful internal categorization to ensure the bank can accurately report these green assets toward their own sustainability disclosures and regulatory requirements. Managing these offerings necessitates transparent communication with consumers, as the primary draw is often the tangible economic benefit coupled with the alignment of personal values and financial behavior. Asset management and wealth divisions are seeing a surge in retail-focused ESG mutual funds and exchange-traded funds designed for individual investors. Unlike institutional mandates that may include complex proxy voting or active engagement strategies, retail ESG funds primarily rely on exclusionary screening, positive impact tilts, or best-in-class selection. Green savings accounts represent another critical product where customer deposits are earmarked specifically for financing renewable energy projects or sustainable infrastructure, rather than being utilized for general corporate lending. Financial institutions must navigate significant operational hurdles here, specifically regarding the traceability of individual capital flows into sustainable projects. Banks manage these risks by implementing rigorous internal tracking systems to prevent any ambiguity regarding where depositor funds are channeled, thereby shielding themselves from potential accusations of greenwashing. Disclosure requirements for these retail products are becoming more stringent, often requiring the bank to present clear, simplified performance data that helps the average investor understand the environmental impact of their specific allocation. Sustainable consumer credit lines are emerging as a niche yet rapidly expanding category, incentivizing personal expenditure on sustainable home improvements or certified sustainable consumer goods. Pricing these products involves a complex interplay between traditional credit risk assessment and the emerging data sets concerning transition risk. If a bank provides a credit line for home efficiency upgrades, they might model the potential improvement in the customer's long-term utility burden, which theoretically improves the consumer's ongoing debt service capacity. However, verifying the environmental impact at the individual household level remains a significant challenge, pushing firms to rely heavily on standardized certification bodies and national energy efficiency databases rather than direct verification. This reliance on third-party verification creates a dependency that institutions must manage, ensuring that their retail products do not inadvertently support carbon-intensive outcomes due to faulty or outdated environmental data. Success in this domain is highly contingent upon the bank's ability to maintain high levels of trust through clear, standardized disclosure practices that translate complex climate impacts into meaningful information for the end user. See you in the next lesson. Welcome back to our discussion on the nuanced landscape of sustainable finance. In this session, we will dissect the mechanical inner workings of ESG ratings and the challenges inherent in current scoring methodologies. ESG ratings are essentially an attempt to quantify the non-financial performance of an organization, yet they are notoriously subjective and opaque. Unlike credit ratings, which benefit from a high degree of correlation between agencies, ESG ratings exhibit significant divergence across major providers. This divergence stems primarily from differences in the scope of indicators, the weightings assigned to specific pillars, and the underlying data sources used for analysis. When an agency assesses a firm, it typically starts by collecting raw data from corporate sustainability reports, public filings, and sometimes direct questionnaires sent to the management. These providers then apply proprietary models to determine what constitutes material information for specific industries, such as prioritizing water usage for agriculture while focusing on data privacy for tech firms. The complexity escalates because each provider has its own philosophical definition of what sustainability truly represents, leading to a situation where a company might be a top performer under one framework and a laggard under another. The architecture of these scores is typically built upon the three core pillars of environment, social, and governance, but the aggregation process is far from standardized. A provider might decide that the environmental pillar should carry double the weight of the social pillar, while a competitor might advocate for an equal distribution across all three. Furthermore, the reliance on self-reported data introduces a feedback loop that often favors larger corporations with the resources to produce elaborate disclosure documents. Small to medium-sized enterprises often struggle to obtain high scores simply because they lack the transparency infrastructure expected by the rating agencies. This structural bias necessitates that practitioners look beyond the headline score and perform a bottom-up analysis of the underlying data points. Relying on an aggregate score without investigating the constituent metrics can lead to a fundamental misunderstanding of the actual sustainability profile a firm presents. Investors and risk managers must treat these ratings as subjective signals rather than objective truths, a reality that has prompted significant regulatory attention. Various jurisdictions are now moving toward creating formal codes of conduct for ESG data and rating providers to increase transparency in their methodology disclosures. The goal is to move away from the current black box environment toward a more comparable and reliable ecosystem where stakeholders can actually understand what a specific score represents. As you navigate these frameworks, you will notice that the index construction industry relies heavily on these ratings to build sustainable funds, which further amplifies the impact of any methodological bias on capital flows. When a specific ESG rating agency changes its scoring model, it can trigger massive rebalancing events in passive investment products, demonstrating just how much influence these private entities exert on market dynamics. Understanding this mechanics is vital for any professional involved in portfolio construction or risk mitigation, as it directly impacts both performance and compliance. See you in our next session. Welcome to our exploration of scenario analysis, where we move beyond historical data to evaluate institutional resilience. In this session, we define the mechanics and conceptual framework of forward-looking climate scenario analysis. Traditional risk management relies heavily on the assumption that the future will resemble the past, using historical data sets to extrapolate potential losses and probabilities. However, climate change defies this dependency, as it involves nonlinear transitions and systemic shifts that have no precedent in modern economic history. We are tasked with quantifying outcomes for scenarios involving drastic changes in carbon pricing, technology diffusion, and geopolitical alignment. Unlike standard value-at-risk models, climate scenario analysis acknowledges that the underlying environment is undergoing a structural change rather than mere stochastic fluctuations. By moving to a forward-looking approach, we detach our risk assessment from the limitations of yesterday and embrace the radical uncertainty of a warming world. We recognize that our statistical models must now account for tipping points and policy mandates that have not yet been fully integrated into market pricing mechanisms. The conceptual design of a climate scenario begins with defining the pathway, which dictates the severity and speed of the physical or transition risk we are measuring. We look at temperature trajectories, typically anchored to the Paris Agreement goals, such as limiting warming to 1.5 degrees or 2 degrees Celsius above pre-industrial levels. These trajectories must be translated into macroeconomic variables, such as fluctuations in GDP growth, changes in commodity prices, or shifts in labor productivity. For instance, a rapid transition scenario implies a steep carbon price path, which forces energy producers to abandon fossil fuel assets prematurely, creating potential balance sheet impairments. We calculate these impacts by mapping the energy mix transformation required to reach net zero by mid-century against current utility and industrial outputs. This allows us to observe how corporate strategies align or diverge from the requirements of a low-carbon economy. When building these models, we must consider the granularity of our inputs, particularly regarding carbon price paths and technological efficiency gains. Carbon pricing acts as the primary transmission mechanism for transition risk, affecting everything from operational costs in manufacturing to the cost of debt for high-emitting enterprises. We then layer energy mix transformations on top of these prices to see how shifts away from coal or gas affect the profitability of specific assets over long time horizons. These long durations are crucial because climate impacts often manifest over decades, far exceeding the typical risk assessment horizon for credit or market risk desks. By stress testing strategies against multiple plausible futures, we determine the robustness of an organization's business model under varying degrees of climate policy stringency. The goal is not to predict the most likely future with precision, but to ensure that the institution remains resilient even under the most challenging, high-impact scenarios. Ultimately, this process forces institutional stakeholders to identify dependencies they might have otherwise ignored. By systematically adjusting climate-related assumptions, such as the speed of electric vehicle adoption or the introduction of cross-border carbon border adjustments, we build a picture of potential institutional fragility. We test how capital allocation responds to these shocks and whether current buffers are sufficient to absorb policy-driven or physical asset impairments. This diagnostic approach turns climate change from an abstract ethical concern into an empirical risk variable capable of being integrated into financial decision-making frameworks. Every scenario acts as a controlled laboratory environment where we observe the interplay between policy, technology, and economic health. Mastering these methodologies is essential for any risk practitioner tasked with navigating the complexities of the current global transition. I will see you in the next lecture. Welcome to this exploration of scenario analysis, where we will rigorously dissect the essential differences between modeling physical risks and transition risks. Understanding these bifurcated approaches is foundational for mastering the quantitative requirements of the SCR exam. When we approach the climate risk landscape, we must distinguish between the physical manifestation of a changing climate and the socio-economic adjustments required to address it. Physical risk scenarios are fundamentally grounded in Earth system models and radiative forcing pathways, capturing the probabilistic severity of hazards. These models operate over long-term temporal horizons, often spanning decades to end-of-century projections, because climate systems evolve slowly relative to human financial cycles. The primary inputs here are greenhouse gas concentration projections, usually represented by representative concentration pathways or shared socioeconomic pathways. We use these to estimate the frequency and intensity of events like wildfires, flooding, or persistent drought. Essentially, we are asking how the physical environment constrains the viability of assets or regional productivity under specific atmospheric carbon loads. By fixing our gaze on these long-term projections, we can stress test capital expenditure plans against scenarios where global warming reaches specific temperature thresholds. In contrast, transition risk scenarios occupy a completely different conceptual space, focusing on the sudden or orderly shift toward a low-carbon economy. These scenarios are inherently human-centric, modeling the impact of policy interventions, technological breakthroughs, and shifts in market demand. While physical risks deal with chemistry and meteorology, Transition risks deal with political economy and industrial strategy. We often employ models provided by institutions like the International Energy Agency to map out specific pathways for energy generation, demand, and grid integration. The time horizons for these models are generally shorter and more granular, focusing on the next 5 to 15 years, as policies and technology adoptions occur in the near term. We are looking at variables like carbon tax implementations, renewable energy subsidies, and the rapid obsolescence of high-emission technologies within specific sectors. The goal here is to determine how a rapid divergence from a business-as-usual trajectory impacts the financial stability of our portfolios. The structural assumptions underlying these two types of scenarios diverge significantly because they serve separate strategic use cases. When we model physical risks, we assume a largely static regulatory environment but a highly dynamic climate, forcing us to consider the resilience of static infrastructure. Conversely, transition modeling assumes a constant level of climate change in the short term, but a highly dynamic regulatory and technological landscape. This means that a transition model is more sensitive to legislative changes, like a sudden hike in carbon pricing, than to the minute fluctuations in global average temperature expected in the next few years. Risk managers must maintain this distinction sharply, as conflating them leads to misaligned capital allocations. Using a transition model to analyze physical risk would result in an underestimation of chronic hazards, just as using a physical model to price carbon risk would fail to account for the speed of policy implementation. By decoupling these models, we gain the precision required to integrate climate change into broader enterprise risk management frameworks. We will see how these disparate logic structures translate into specific analytical outcomes in the following sessions. See you in the next lecture. Welcome back. In this session, we will examine the Network for Greening the Financial System Scenario Framework to understand how central banks and supervisors model long-term climate risk. The Network for Greening the Financial System, or NGFS, provides a standardized set of scenarios that serve as a common language for financial institutions when assessing climate-related risks. These scenarios are designed to help firms look beyond historical data, which is often insufficient for predicting the impacts of a changing climate. By framing potential pathways for future emissions and policy interventions, these scenarios allow banks, insurers, and asset managers to stress test their portfolios against varying levels of transition and physical risk. The NGFS framework relies on integrated assessment models to bridge the gap between complex climate science and financial decision-making processes. It is essential to recognize that these are not forecasts, but rather exploratory tools used to assess resilience under different hypothetical futures. When you are analyzing a portfolio using these data sets, you are essentially asking what would happen to your assets or liabilities if one of these specific pathways were to materialize over a period of up to 30 years. The framework is inherently forward-looking and requires institutions to translate macroeconomic variables, such as carbon prices and GDP growth, into credit or market risk metrics. The first quadrant of the NGFS framework is the orderly transition scenario, which assumes that climate policies are introduced early and become progressively more stringent over time. In this scenario, global temperature increases remain well below 2 degrees Celsius, and the transition to a low-carbon economy is managed in a smooth, predictable manner. Because policy changes are anticipated by market participants, capital remains mobile and can be reallocated efficiently towards sustainable technologies without causing sudden, systemic financial shocks. The orderly scenario typically results in lower transition risk for companies in carbon-intensive sectors, as they have adequate time to adjust their business models and invest in new operational efficiencies. From a financial modeling perspective, this results in stable, albeit higher carbon prices that are fully internalized by the market. Consequently, banks using this scenario usually forecast lower long-term impairment of loans held in traditional energy or heavy manufacturing sectors. It serves as a benchmark for what a successful mitigation strategy looks like when both governments and the private sector act in concert. Conversely, the disorderly transition scenario reflects a reality where policy actions are either delayed or implemented in a sudden, disjointed fashion. This often occurs when governments choose to ignore early warning signs, forcing them to introduce drastic and rapid shifts in regulation once a climate threshold is approached. Because the market has little time to adjust to these sudden changes, we often see significant volatility in asset prices and severe disruption to supply chains. The disorderly transition introduces a high degree of transition risk, as companies that were previously considered viable suddenly find their cost of capital rising sharply due to high, unexpected carbon taxes or sudden bans on fossil fuel operations. For a financial institution, this creates a situation where the rapid repricing of assets could lead to fire sales or liquidity shortages in specific segments of the market. This scenario highlights the dangers of climate policy uncertainty, showing how delayed action shifts the burden of adjustment from a gradual process to an acute financial crisis. Managing exposure under this scenario requires firms to maintain higher capital buffers and conduct more rigorous counterparty credit analysis. The hot house world scenario represents a future characterized by insufficient climate action and a failure to meet the goals of the Paris Agreement. In this pathway, policies are either non-existent or inadequate, resulting in a temperature trajectory that significantly exceeds the 2-degree threshold. The primary risks within this scenario are not related to policy changes or carbon pricing, but rather to the devastating physical impacts of climate change. As global temperatures rise, the frequency and severity of extreme weather events, such as heat waves, floods, and wildfires, increase significantly, leading to chronic physical risk. For institutional investors, this means the permanent impairment of physical assets and the degradation of natural capital that supports economic activity. Insurance premiums may become prohibitively expensive, leading to a potential protection gap where large swaths of property become uninsurable and essentially stranded. This scenario effectively tests a portfolio for its resilience to long-term chronic physical damage and the cascading systemic impacts of a destabilized global environment. Finally, the too little, too late category serves as a distinct variation that acknowledges the reality of partially implemented policies followed by a late-stage, frantic attempt to catch up. This pathway attempts to balance some, but not all, of the risks associated with both physical and transition factors. It underscores the difficulty of managing two competing pressures simultaneously: the pressure to mitigate emissions through late-stage intervention and the pressure to adapt to the physical realities of an already warming world. The NGFS provides these standardized scenarios so that financial institutions can report consistent information to regulators and shareholders about their exposure to these divergent futures. Operationalizing these scenarios involves mapping sectoral GDP and risk variables provided by NGFS onto an institution's own internal risk management systems. By using these common scenarios, firms ensure that their climate risk disclosures have a foundational consistency, which allows for better peer benchmarking and supervisory oversight. It is through this granular mapping process that an institution translates abstract climate pathways into concrete balance sheet impacts. I will see you in the next lecture. Welcome back. Today we examine the mechanics of climate stress testing as a vital tool for institutional solvency and risk governance. Climate stress testing represents a departure from traditional financial stress testing because it must account for long-horizon uncertainties that deviate significantly from historical data patterns. Unlike standard stress tests that rely on past volatility to project short-term outcomes, climate stress testing requires mapping complex macroeconomic climate scenarios onto specific financial risk drivers. We begin by translating climate pathways, such as those provided by the NGFS, into variables that resonate with credit risk models. For example, a disorderly transition policy that imposes sudden carbon pricing will directly impact the cost of production for high-emission counterparties. This cost pressure diminishes the debt servicing capacity of those firms, which necessitates a quantitative adjustment to their probability of default metrics. As an analyst, you must recognize that these impacts are rarely linear and often manifest through cascades across industries. The translation layer from macroeconomic shocks to individual credit risk metrics forms the core of an effective stress testing framework. When we assess an institution's portfolio, we are specifically looking at how shifts in climatic conditions or policy environments alter the financial statements of our borrowers. By adjusting the probability of default and the loss given default assumptions under stress, we generate a forward-looking view of potential credit deterioration. This process often involves multi-step modeling, where physical risk factors, such as extreme weather events or chronic sea level rise, lead to asset write-downs or operational disruptions for the counterparty. We then translate these operational losses into a probability of default shift, recognizing that a firm's solvency is inextricably linked to the physical resilience of its assets. This rigorous mapping ensures that the stress test captures the institutional exposure rather than just theoretical macroeconomic tailwinds. At the portfolio level, these risk aggregations must account for temporal dynamics that extend far beyond the typical 2 to 3 year stress testing cycle. While traditional capital adequacy assessments usually look at short-term solvency, climate risk requires us to evaluate capital requirements over decadal timeframes where climate impacts become non-negligible. This long horizon approach forces us to reconcile the mismatch between the longevity of physical climate risks and the liquidity horizons of many banking loan portfolios. We evaluate systemic risk concentrations where multiple industries might face synchronous shocks, such as a sharp decline in fossil fuel asset values affecting both energy producers and their downstream logistics partners. Consequently, regulators are increasingly mandating that financial institutions demonstrate their ability to withstand these scenarios by maintaining sufficient capital buffers to absorb potential climate-related shocks. Evolving regulatory frameworks globally now emphasize that climate stress testing is not just a compliance exercise, but an integral component of enterprise-wide capital management. Prudential supervisors expect institutions to move beyond simple sensitivity analysis toward a comprehensive understanding of their institutional solvency under various representative concentration pathways. You should focus on how these tests inform strategic decisions, such as sector-specific lending limits, or the diversification of assets into more resilient geographical regions. Understanding how to model loss given default in a climate-stressed environment requires you to reconsider the valuation of collateral, especially when that collateral is susceptible to physical hazards like floods or wildfires. Effectively executed, this stress testing process provides a dynamic feedback loop that allows the firm to optimize its risk appetite while navigating the underlying structural changes of a warming global economy. I will see you in our next session. Welcome back to our journey through the SCR curriculum. Today, we turn our focus to the operational reality of embedding climate considerations into the bedrock of modern finance, enterprise risk management. Integrating climate risk into an existing enterprise risk management system is not a matter of simply appending a new asset class to a ledger. It requires a fundamental reconciliation between the fluid, long-term nature of climate change and the fixed, cyclical nature of corporate governance. Traditional risk management operates on horizons that rarely exceed 3 to 5 years, whereas climate models often demand visibility across several decades. Bridging this gap requires organizations to redefine their internal risk taxonomies to ensure that climate-related hazards, whether physical or transitional, are not treated as isolated externalities. By formalizing these risks within a standard taxonomy, firms enable a common language that risk managers, business unit leads, and the board can use to discuss exposure with equal clarity. This, in turn, allows for the explicit inclusion of climate risk within the formal risk appetite statement of the organization. Effective governance relies heavily on the classic three lines of defense model, which must be adapted to account for the unique characteristics of climate risk. The first line, composed of business units and functional management, must now take active ownership of climate-related exposures in their daily lending or production decisions. The second line, typically the risk management and compliance functions, must facilitate this by updating internal credit policies and risk assessment methodologies to reflect climate vulnerabilities. For instance, updating a commercial lending policy might involve requiring physical risk assessments for collateral located in high-risk zones, such as areas prone to chronic sea level rise. Finally, the third line, internal audit, must ensure that the methodologies used to quantify and monitor these risks remain robust and unbiased. Assigning executive ownership is perhaps the most critical step in this governance structure, as it ensures that the visibility of climate risk is elevated to the highest levels of the organization. Reporting mechanisms serve as the central nervous system of any sound risk management architecture, and they require significant refinement for climate risk. Senior management and the board of directors require reporting that is tailored to their oversight responsibilities, meaning they need a distilled overview of material exposures rather than exhaustive raw data. This requires establishing standardized internal metrics that can survive the inherent uncertainty of climate modeling. Firms must be careful to avoid the trap of over-precision. While quantitative metrics are valuable, the qualitative narrative regarding transition strategies often provides the board with more actionable intelligence. These reports should reconcile climate-related vulnerabilities with the overall financial health of the firm, allowing directors to weigh climate risk against other traditional risks like liquidity or operational failure. Without this robust internal reporting mechanism, climate risks remain siloed, preventing the holistic decision-making necessary for the firm to remain resilient in a changing global economy. Many organizations encounter significant friction when attempting to synchronize these new reporting requirements with their existing operational rhythms. Because climate risks evolve slowly, they may fail to trigger conventional risk alerts that are designed for immediate, short-term volatility. This necessitates a move toward forward-looking analytical tools rather than historical trend analysis, which is inherently backward-looking and insufficient for predicting the systemic shifts associated with global warming. Governance frameworks must therefore incorporate scenario-based assessments that look beyond the immediate fiscal year, forcing planners to build long-range resilience into their strategy. By embedding these forward-looking indicators into the existing board-level agenda, the firm ensures that climate risk is not an afterthought, but a core component of the business model. This integration, while operationally taxing, is the primary mechanism by which an institution effectively manages its long-term viability in the face of climate change. Catch you in the next one. Welcome back to our journey through the complexities of climate-related financial risk management. Today, we turn our attention to the quantitative heart of the matter by evaluating the metrics and targets used to oversee climate exposure in our portfolios. When we manage an investment or lending portfolio, we are essentially managing a collection of future cash flows that are increasingly sensitive to climate variables. Understanding these exposures requires a shift from traditional financial ratios to metrics that capture the nonlinear relationship between carbon output and capital stability. We start by looking at capital allocation metrics, which help us determine how much of our risk budget is tied up in carbon-intensive assets. This is not merely about identifying who emits the most, but about gauging the degree to which business models depend on fossil fuel rents that may depreciate rapidly. By integrating these metrics, a manager can move beyond superficial ESG screening and begin to quantify the capital loss associated with mandatory carbon pricing or regulatory interventions. We categorize these metrics based on their ability to capture historical emissions versus their effectiveness in predicting future risk exposure. Portfolio carbon footprints represent the most common starting point for most financial institutions in this space. This metric aggregates the weighted average carbon intensity of the individual assets within the portfolio to provide a snapshot of total exposure. While calculation methods vary, the core mechanism involves multiplying the portfolio weight of each holding by its carbon intensity, commonly measured as tons of carbon dioxide equivalent per $1 million of revenue. However, a footprint is a lagging indicator. It tells us what happened in the past, but does not inherently predict how a company will fare under a net zero transition. To address this, we must look at carbon asset risk indicators that flag assets with high sensitivity to specific transition policy outcomes. These indicators act as early warning systems, allowing for rebalancing before an asset becomes a stranded liability on the balance sheet. To bridge the gap between static footprints and future risk, we utilize implied temperature rise or ITR metrics. This methodology seeks to estimate the global warming pathway that would occur if the entire global economy followed the same decarbonization trajectory as a specific company or portfolio. By mapping emissions reduction commitments against global carbon budgets, ITR provides a forward-looking alignment percentage that is much more intuitive for stakeholders than raw emission counts. It is a powerful tool, yet we must remain cognizant of the underlying assumptions regarding technological transition and offset reliability. When these metrics indicate a divergence from 1.5-degree alignment, it triggers a management response to mitigate transition policy risks through divestment, engagement, or hedging strategies. Consequently, these tools allow us to move from passive reporting to an active, science-based stewardship of our underlying assets. Risk management in this context also requires careful monitoring of concentration metrics within sensitive sectors. Many portfolios suffer from hidden concentrations in energy, utilities, and heavy manufacturing that appear diversified on the surface, but are highly correlated in a climate stress event. By applying concentration limits to carbon-intensive sectors, we prevent accidental risk buildup that could threaten the liquidity of the entire ledger during a sudden market shift. We also rely on climate-adjusted valuations, which attempt to price in the projected costs of carbon taxes and energy transition mandates directly into our cash flow forecasts. This integration is vital for ensuring that our performance targets are realistic, given the changing regulatory and physical landscape of the next decade. Success here involves aligning our portfolio metrics with formal institutional targets, such as those set through the Science-Based Targets Initiative, to ensure consistency and accountability. As we continue to refine these methodologies, remember that consistency in reporting is as important as the accuracy of the underlying data. Whether you are adjusting for Scope 3 emissions or refining your approach to ITR calculations, the goal remains the same: providing a clear, defensible narrative of risk exposure. Effective risk mitigation depends on your ability to synthesize these diverse metrics into a coherent strategy that balances profitability with the reality of a transitioning global economy. See you in our next session. Welcome back. In this session, we will examine the Task Force on Climate-Related Financial Disclosures framework, which functions as the primary blueprint for how modern organizations communicate climate risk. The TCFD was established to address a systemic transparency gap, where investors lacked consistent data to price climate-related risks correctly. By providing a structured approach, it creates a common language for disclosures that moves beyond qualitative sustainability narratives into actionable financial metrics. We observe that this framework is increasingly becoming the bedrock for mandatory reporting regimes across major jurisdictions, meaning its importance for both public and private entities is absolute. The framework rests on four pillars that intersect with traditional financial reporting, ensuring that climate intelligence is integrated into the core of corporate decision-making rather than relegated to sideline marketing reports. Mastering these pillars is not merely a task of rote memorization for the exam, but essential for understanding how capital allocation is shifting toward net zero alignment. The first pillar is governance, which requires the organization to clearly define the role of the board and management in overseeing climate risks and opportunities. It is not enough to name a sustainability officer, as the framework insists on evidence that climate concerns reach the highest levels of corporate strategy. You must be able to demonstrate that institutional structures are in place to vet and act upon climate findings periodically. This pillar asks for transparency regarding the frequency and depth of board discussions concerning climate-related matters. When we look at corporate disclosures, we look for explicit mentions of how the board monitors progress against targets. A well-governed firm treats climate risk with the same rigor as it treats liquidity or credit risk. Moving into the second pillar, we discuss strategy, which forces an organization to assess how climate-related issues actually impact their business models under different scenarios. This is where the framework becomes quite practical, as it demands an evaluation of potential impacts over short, medium, and long-term horizons. A key requirement here is the use of scenario analysis to test the resilience of the current business model against diverse climate outcomes. If a company fails to map out these risks, they are essentially ignoring the potential for stranded assets or rapid changes in demand. This pillar highlights the necessity of linking climate strategy to the actual financial planning process of the firm. It ensures that the transition to a low-carbon economy is considered a strategic driver rather than an external nuisance. The third pillar focuses on risk management, or specifically the processes the entity employs to identify, assess, and manage these climate risks. This implies a transition from general storytelling to the systematic integration of climate factors into the existing enterprise risk management system. For the exam, recognize that disclosure requires a clear description of how the organization prioritizes risks, especially distinguishing between climate risks and other traditional categories. One must show that there is a documented process for deciding which climate issues carry the most materiality and financial weight. It is not enough to identify that a risk exists. The framework requires disclosures on how that risk is being mitigated and integrated into overall risk strategy. This pillar bridges the gap between high-level policy and day-to-day operational safety. The final pillar concerns the metrics and targets that a firm utilizes to assess and manage relevant climate-related risks and opportunities. This is the quantitative heartbeat of the TCFD, where firms must disclose the specific data points used to track performance, such as Scope 1, 2, and potentially 3 greenhouse gas emissions. You should understand that these metrics must be consistent across reporting cycles to ensure comparability for investors attempting to benchmark different firms within the same industry. Beyond mere carbon accounting, this pillar demands that firms describe the targets used to manage climate risks and performance against those specific targets. Without hard data, the rhetoric of sustainability remains unverified, which is why regulators are insisting on robust, auditable targets. By aligning reported metrics with strategic goals, firms provide the necessary signal to the market regarding their progress toward decarbonization or climate adaptation. See you in the next lecture. Welcome back. In this session, we investigate the harmonization of global sustainability reporting through the work of the International Sustainability Standards Board. The landscape of corporate reporting has historically been fractured, with a proliferation of voluntary frameworks creating significant noise for investors and analysts. The emergence of the International Sustainability Standards Board, or ISSB, represents a deliberate push toward a singular, investor-grade global baseline for sustainability disclosure. By consolidating the legacy frameworks established by the Sustainability Accounting Standards Board and the Climate Disclosure Standards Board, the ISSB aims to bridge the gap between financial accounting and sustainability disclosure. This is not merely an administrative exercise, but a fundamental shift in how corporations must quantify and communicate their exposure to sustainability-related risks. Understanding these standards is critical for the exam, as they currently represent the most objective benchmark for global regulatory compliance. We will look closely at how these requirements formalize the integration of non-financial data into traditional financial reports. By mastering the core components of these standards, you will gain the ability to evaluate whether a firm's environmental reporting meets the threshold for institutional decision-making. At the center of this consolidation are two foundational documents known as IFRS S1 and IFRS S2. IFRS S1 establishes the general requirements for disclosing sustainability-related financial information, placing the emphasis on materiality from the perspective of the primary users of general-purpose financial reports. It requires reporting entities to disclose information about all sustainability-related risks and opportunities that could reasonably be expected to affect the entity's cash flows or access to finance. This standard effectively insists that sustainability is no longer a separate exercise meant for branding, but a core component of the organization's financial risk profile. It mandates a connection between sustainability disclosures and the entity's financial statements, ensuring that the two narratives are not only consistent, but mutually supporting. When you are analyzing an organization under these rules, you should consider whether the disclosed information is decision useful and whether it highlights the risks that would realistically threaten the firm's long-term enterprise value. Building upon the general requirements laid out in S1, IFRS S2 narrows the focus specifically to climate-related disclosures. This standard retains the core four pillars first popularized by the TCFD framework, effectively codifying them into a mandatory global language for climate reporting. It requires firms to detail their governance processes, their strategy for navigating climate-related risks, their risk management procedures, and the specific metrics and targets used to monitor their transition. For example, a company must now clearly explain how climate-related scenarios, such as a disorderly transition to a 2-degree warming pathway, would specifically impact their operational costs and capital expenditure. This requires a level of quantitative rigor that was not strictly enforced under previous voluntary regimes. By moving these considerations into the financial reporting cycle, the ISSB ensures that climate risk is subject to the same oversight and audit scrutiny as traditional financial liabilities. The transition from a landscape of fragmented standards to the ISSB baseline has profound implications for how we view data consistency. Previously, firms could select the framework that best presented their sustainability performance, which often resulted in strategic reporting aimed at highlighting positive outcomes while burying systemic risks. The ISSB removes much of this discretion by anchoring disclosures to the financial cycle, which significantly increases the comparability of data across jurisdictions. As an analyst or a risk manager, this consolidation simplifies the task of benchmarking firms, as you are now comparing data derived from a shared structure rather than disparate frameworks. This evolution is particularly important when evaluating entities that operate across multiple geographies, as the ISSB baseline is designed to be globally interoperable. It is vital to recognize that while these standards are inherently financial, they require deep domain knowledge of how environmental variables can translate into material fiscal loss. When looking at the operational mechanics required by IFRS S2, it is useful to think about the distinction between transition risks, such as policy shifts or reputational damage, and physical risks, such as operational disruptions from extreme weather events. The standard demands that these categories be quantified with as much precision as possible, moving beyond vague commitments into hard, audited metrics. This effectively places the burden of proof on the corporation to demonstrate that they are integrating climate scenarios into their capital allocation logic. In practice, this means we expect to see clear evidence of how a firm's stated net zero targets align with its multi-year investment plans. If a firm reports a commitment to reduce carbon intensity but simultaneously approves large-scale capital investments in legacy high-carbon assets, the discrepancy would now be far more visible to regulators and stakeholders. This transparency is the core objective of the ISSB, and it forms the bedrock for modern institutional investor requirements. See you in the next lecture. Welcome back. Today we examine the technical methodologies for calculating Scope 3 Category 15 emissions, which represent the carbon footprint of an institution's financial activities. When we talk about measuring financed emissions, we are essentially looking at how a financial institution attributes the greenhouse gas emissions of its clients or investees to its own balance sheet. This process is grounded in the Partnership for Carbon Accounting Financials, or PCAF, Global GHG Accounting and Reporting Standard. The fundamental principle here is attribution, which allows a lender or investor to calculate their specific share of a borrower's emissions based on the proportion of the financing provided relative to the total value of the borrower. Without this standardization, comparing the climate impact across different portfolios or financial institutions would be functionally impossible, as firms would use disparate metrics to claim progress. By calculating these figures, institutions gain the transparency necessary to manage climate-related transition risks and align their portfolios with net zero pathways. This accounting is not merely a reporting exercise, but a core diagnostic tool for institutional capital allocation decisions. The calculation methodology varies depending on the specific asset class involved, reflecting the unique nature of the exposure to the underlying entity. For listed equity and corporate bonds, you typically multiply the emissions of the investee by an attribution factor, which is defined as the ratio of the outstanding investment amount to the total enterprise value, including cash of the borrower. Business loans are treated similarly, though the denominator shifts to reflect the total equity and debt funding of the company. Commercial real estate presents a slightly different challenge because the primary driver of emissions is the energy consumed by the building itself. Here, you often calculate the emissions based on floor area or energy utility data, attributed to the lender based on the outstanding loan amount relative to the property value at the time of origination. Project finance requires a project-specific approach where the emissions intensity of the project, such as a wind farm or a coal plant, is mapped directly to the lender's share of the total project cost. Data quality remains a persistent challenge in this field because not all corporations disclose their Scope 1, 2, and 3 emissions with the same level of granularity or frequency. PCAF addresses this disparity through a rigorous data quality scoring framework that ranks information from 1 to 5, where a score of 1 represents verified actual emissions data and a score of 5 represents the lowest quality estimate based on spin-based proxies. When an institution lacks primary data, they must rely on these proxy methods, which inevitably introduce a degree of uncertainty into the carbon accounting process. Over time, as regulatory requirements increase and corporate reporting improves, the objective is to migrate all portfolio assets toward a score of 1. This framework allows institutions to document exactly where their data is weak, providing a transparent basis for engaging with investees to improve their internal emission monitoring and disclosure practices. Managing these gaps effectively is as much about data governance as it is about environmental science, requiring a systematic approach to identifying where estimates are substituting for hard facts. Understanding these mechanics is essential for the exam because they define the boundary between what an institution is responsible for and what they are not. The specificity of the attribution factor ensures that a bank does not mistakenly report the entire emissions output of an industrial plant if the bank only financed a small fraction of the capital investment. These calculations serve as the denominator for future climate scenario stress tests and are the primary input for setting science-based targets. When you are analyzing these scenarios, you must be able to distinguish between physical asset emissions and the financial share attributed to the lending entity. Failure to correctly apply these formulas can lead to significant discrepancies in impact reporting, which is a major red flag in green finance. As you move forward, keep these attribution logic patterns in mind, as they form the bedrock of transparent sustainability reporting within the financial sector. See you in the next lecture. Welcome back to our technical deep dive into the quantitative aspects of climate risk management. Today, we focus specifically on the rigorous methodologies required for carbon accounting. Carbon accounting provides the numerical foundation upon which an organization assesses its environmental footprint and external impact. According to the Greenhouse Gas Protocol, accounting begins with the categorization of emissions into three distinct scopes, which are essential for avoiding double counting. Scope 1 covers direct emissions from owned or controlled sources, such as company vehicles or on-site manufacturing combustion. Scope 2 accounts for indirect emissions from the generation of purchased electricity, steam, heating, and cooling consumed by the reporting entity. Scope 3 represents the complex web of emissions occurring in the value chain, ranging from purchased goods and services to the end-of-life treatment of sold products. Mastering these distinctions allows a risk manager to transform raw operational data into verifiable environmental disclosures that satisfy regulatory scrutiny and investor expectations. When we shift from reporting absolute emissions to analyzing financial risk, we utilize normalization techniques to create comparable metrics. A simple absolute emission total, measured in metric tons of carbon dioxide equivalent, tells us little about the efficiency or the risk profile of a firm relative to its peers. By normalizing the carbon footprint against market value or corporate revenue, we arrive at a more granular view of carbon efficiency. For instance, expressing emissions per $1 million of revenue allows a stakeholder to observe how successfully a company detaches its financial growth from its environmental impact. This process of intensity calculation is a cornerstone of modern portfolio management because it highlights firms that are overexposed to carbon-intensive operations relative to the value they generate for shareholders. The most critical quantitative tool for portfolio risk assessment is the weighted average carbon intensity, commonly referred to as WASI. Unlike a simple average, WASI provides an investor with a snapshot of their exposure to carbon-intensive companies by weighting each company's individual carbon intensity by its portfolio weight. To calculate this, you take the carbon intensity of each underlying company in your portfolio, defined as absolute emissions divided by total revenue, and multiply that figure by the portfolio weight of that specific security. By summing these individual products, you arrive at a single metric that represents the portfolio's aggregate carbon efficiency. This allows risk managers to pinpoint exactly which assets are driving the portfolio's aggregate emission exposure, thereby enabling more precise divestment or engagement strategies. Mathematical rigor in these calculations is not merely an exercise in accounting, but a fundamental requirement for regulatory compliance and effective climate transition planning. When reporting, you must ensure that the carbon intensity of an issuer is normalized consistently across the entire portfolio. If you mix revenue-based intensity with market capitalization-based intensity, the resulting sum becomes meaningless and potentially misleading to stakeholders. Furthermore, because Scope 3 emissions represent the vast majority of carbon risk for many sectors, the decision to include or exclude them in your calculations must be clearly documented. Transparency regarding the methodology and the boundaries set for these calculations is as important as the final figure itself, as it dictates the credibility of your risk disclosures. Ultimately, these metrics serve as a proxy for physical and transition risk exposures within an investment universe. A high WASI score suggests that a portfolio is significantly vulnerable to regulatory shifts like carbon taxes or technological shifts that favor low-carbon competitors. Conversely, monitoring changes in these metrics over time reveals the efficacy of a carbon reduction strategy at the firm level. By calculating carbon footprints with precision, you move beyond the static reporting required by regulators to building an active risk management framework. You are creating a tool that identifies capital allocation risks in a decarbonizing global economy, ensuring that your portfolio positioning aligns with both fiduciary duties and long-term climate objectives. See you in the next session. Welcome back. In this lesson, we will examine the structural components and strategic imperatives required for credible corporate net zero transition planning. A net zero transition plan functions as a roadmap for an organization to align its business model, operations, and entire value chain with the goal of limiting global warming to 1.5 degrees Celsius. This is not merely an exercise in carbon accounting, but a fundamental shift in capital allocation and operational strategy that requires oversight at the highest level of governance. When an enterprise develops a transition plan, it must define clear interim targets that are scientifically grounded, typically aligning with pathways validated by the Science Based Targets Initiative. Without these granular milestones, the long-term claim of achieving net zero by mid-century remains speculative and vulnerable to accusations of greenwashing. These targets necessitate a breakdown of emissions into Scope 1, 2, and 3 categories, requiring a comprehensive assessment of the organization's carbon footprint throughout its upstream and downstream activities. Effective plans identify specific decarbonization levers, such as shifting energy procurement to renewables, optimizing supply chain logistics, or re-engineering product development to favor low-carbon materials. Beyond these operational changes, the plan must articulate how the underlying financial structure of the company will pivot away from high-carbon assets that risk becoming stranded as the regulatory environment tightens. This strategic reallocation of capital ensures that the firm remains solvent and competitive in a transition scenario where carbon prices are likely to escalate significantly. Governance of these metrics requires integration into the existing enterprise risk management framework, rather than treating sustainability as a peripheral concern. The board must hold executive management accountable for the delivery of these transition goals, linking performance incentives to the achievement of specified emission reductions alongside traditional financial KPIs. When we view these plans through a risk management lens, the motivation for adoption extends well beyond simple compliance with emerging mandatory disclosure requirements. Organizations face a distinct threat to their long-term cost of capital if they cannot demonstrate to institutional investors that they are prepared for a low-carbon economy. Maintaining market access requires transparency, as financiers and credit rating agencies increasingly incorporate transition plan maturity into their assessment of creditworthiness and default risk. Furthermore, there is a significant reputational risk associated with the perception of inertia, where stakeholders may interpret a lack of a clear, actionable path to net zero as a sign of management incompetence or strategic blindness. Conversely, early adoption positions a company to capture competitive advantages, such as lower energy costs after efficiency improvements and the identification of new, sustainable product lines that meet evolving consumer preferences. By treating the transition as an industrial transformation rather than a reporting obligation, firms can mitigate the risk of litigation and regulatory intervention while simultaneously exploring new market opportunities. The complexity of these plans often stems from the necessity of integrating diverse business units, each with different operational footprints and decarbonization potentials. A manufacturing facility will have a vastly different set of transition actions compared to a financial services firm or a software developer. Therefore, institutionalizing the transition requires bespoke strategies that acknowledge these operational nuances while adhering to a unified, company-wide carbon reduction objective. Credibility is established through the disclosure of the organization's current state, the projected pathways, and the specific technology or policy assumptions being utilized to achieve the stated reductions. Because these forecasts rely on external factors, such as the scale-up of carbon capture technology or the pace of grid decarbonization, sensitivity analysis regarding these assumptions is essential. Organizations must be able to demonstrate that they understand their own reliance on these variables and have contingency plans for scenarios where technology adoption or policy support lags behind expectations. When a plan is presented to stakeholders, it should provide a degree of confidence that is commensurate with a financial budget, demonstrating that the management team has thoroughly stress-tested their path to viability. This level of rigor elevates the transition plan from a marketing document to a governance instrument that informs every major capital expenditure decision. See you in the next lecture. Welcome back. This final lesson brings together every thread we have woven throughout our journey to synthesize a cohesive mastery of the GARP SCR curriculum. We started by examining the physical foundations of climate change, grounding our understanding in the hard data provided by the IPCC regarding global warming potentials and the delicate stability of planetary tipping points. It is crucial to view these scientific realities not as isolated academic phenomena, but as the underlying drivers of tangible financial and transition risks. When you consider geographical vulnerabilities or the economic consequences of mitigation efforts, you are essentially performing a risk assessment of the global biosphere. By understanding the Earth's feedback loops, you create a baseline that allows you to differentiate between short-term market volatility and long-term structural shifts. This internal mental map serves as your primary defense when evaluating climate-related disclosures in a professional capacity. The physical reality of the changing climate dictates the constraints within which all future economic and policy decisions must operate. Consequently, your ability to articulate these scientific concepts is the foundation upon which your financial analysis must be built, ensuring that your risk identification process is both technically accurate and practically relevant. Moving beyond the science, we explored the complex landscape of policy architectures and sustainability frameworks that define the modern regulatory environment. The evolution from early sustainability concepts toward the sophisticated landscape of nationally determined contributions and international agreements highlights a clear trend toward stricter compliance and transparency. Whether analyzing carbon taxing mechanisms or the nuances of cap-and-trade systems, the key is to recognize that policy is a material driver of transition risk and market shift. You have observed how green taxonomies and standardized reporting requirements, such as those formalized under the TCFD and ISSB, are transforming vague ESG aspirations into quantifiable data points. Integrating this into an enterprise risk management framework is no longer a niche activity for sustainability departments, but a core competency for modern finance professionals. By mastering the ability to identify greenwashing tactics, you distinguish actual institutional progress from superficial marketing, which is a vital skill when conducting due diligence. Understanding the regulatory tailwinds and the institutional shift toward a circular economy will remain the most reliable indicator of where capital allocation will flow in the coming decade. When we turned our attention to the metrics of finance and risk management, we focused on the methodology of scenario analysis as the primary tool for navigating an uncertain future. You have learned to distinguish between NGFS scenarios and bespoke climate stress tests, recognizing that these are not crystal balls, but sophisticated constructs used to model resilience under varying temperature pathways. Measuring financed emissions and applying rigorous carbon accounting calculations allow firms to quantify their climate exposure with a level of precision previously thought impossible. These metrics, coupled with the proper utilization of ESG ratings, provide the quantitative substance required for sound decision-making in sustainable finance. Remember that portfolio metrics and targets are most effective when they are integrated into a broader net zero transition plan that explicitly recognizes potential stranded assets. As you prepare for the examination, think of these tools as a unified toolkit designed to translate scientific and policy externalities into standard risk management language. Your proficiency in these techniques is what separates a passive observer from a strategic participant in the transition to a low-carbon economy. For the examination itself, prioritize the synthesis of these domains over rote memorization of isolated facts. Success often hinges on your ability to apply the TCFD framework to a case study scenario by identifying how governance, strategy, risk management, and metrics overlap in a specific corporate context. High-yield learning objectives will repeatedly ask you to link a physical risk, like increased frequency of extreme weather events, to its specific impact on a company's operational capability and institutional balance sheet. During the exam, focus on the causality chain. The scientific forcing leads to policy intervention, which shifts capital markets, eventually manifesting as credit, market, or operational risk. If you can maintain this perspective, you will be able to dissect even the most complex case studies by anchoring your answers in the fundamental tenets we discussed. Remain calm. Read the nuances of the question, prompts carefully, and trust the logical framework you have developed. This structured approach to risk identification and reporting is the ultimate goal of the certification, and it is exactly what will be tested on your path to becoming an expert in this field. I wish you the best of luck on your upcoming exam.